to soft core processor. Embedded system design using NIAS2. We had the hardware design. We are going to see the hardware design as well as the software design. And we complete the embedded system using the NIAS. And we are going to get into the golden hardware reference designs that are available and golden system reference designs which are available, which are the GSRD designs. And we have the embedded system design using Cyclone 5 and ARM, how to make communication between the hard processor system and the FPGA. We had a discussion on simulation and debug. Yesterday, we discussed about the signal tap logic analyzer. That was verifying a small memory. Today, how we are going to verify an SOC, right? So we wanted to apply some debugging techniques to ensure that the design, what we have done in the platform designer, is completely verified. So in order to ensure that the debugging techniques are performed very well, we wanted to introduce signal tap and then system console. So signal tap has been introduced to you yesterday. Today we will have more discussion on the system console debugging technique tool. We have 2-3 examples on implementation of the SOC board, and I will also introduce you about how do we perform the lab demo and then the hands-on lab. There are hands-on lab that are present in the afternoon, which we can discuss in detail. So let us start the session with a quick introduction to Intel SoC FPGAs. What is a system on a chip? Let us understand that in detail, and then we will move on to the rest of the topics. The system on a chip, an SoC, it is an IC designed by stitching together multiple standalone VLSI designs to provide full functionality for an application. In SoC, an ASIC vendor may use a library of cores designed in-house, as well as some cores from fabless or chipless design houses, also known as intellectual property companies. When we were discussing about the intellectual property, so we have seen what are the Intel intellectual property cores, and we instantiated that IP into the design, and we generated the design. So now what we wanted is, we don't want to develop the RTL. Instead, we wanted to create a system based on the intellectual property. That means we are going to perform an SoC which is based on the IP core. That means it is an IP core based system on a chip design. That's what we are going to perform today. The question to us is, why do you want to perform an SoC system on a chip? What is the advantage of having an IP core based system on a chip design? What are the application areas of this SoC? Right? Once we get an idea of how those SoC FPGAs and how they could be targeted for variety of applications, it would be easy for us to understand the architecture of the SoC FPGA and appreciate the hardware and software design flow. So let us get into the details right now. Let us go through the basic applications of the system on a chip, where we use that in day-to-day life. Cell phones use several programmable processors to handle the signal processing and the protocol tasks required by telephony. Now, when you say that it uses several programmable processors, that is there, and what is the necessity of utilizing that? When you say these architectures must be designed to operate at the very low power levels provided by batteries. Now, what is very important for us is, like, we wanted several programmable processors. That is number one. The second thing is, we have to handle the signal processing and the protocol tasks. That means inside the mobile phone, we have to handle different signal processing and protocol tasks. And also, what is very important characteristic there is that very low power levels provided by the batteries. Right? We are just commenting on the battery backup in terms of mobile phones, right? So that is very important for us to understand. The second thing is the telecommunications and networking use specialized system on chip, such as network processors, etc., to handle huge data rates. What is very important, the other characteristic is, when we are taking care of the telecommunication and networking, we need to handle huge data rates on the other side. The third one, if we see, the digital television and set-top boxes, when we go through their kind of features, we use sophisticated multiprocessors to perform real-time video and audio decoding and user interface functions. So in our case, we have to see that the specific thought processes is we have to ensure that we should perform real-time video and audio decoding and user interface functions. In the television production equipment, we use system on chips to encode video. Encoding high definition video in real time requires extremely high computation rate. So what is another important feature and thing we have to go through is we require to encode video, and the main important logic what we need to keep in mind is that it is high definition video that is required to be done in real time, and that requires extremely high computation rates. And now the video games use several complex parallel processing machines to render gaming in real time. Wanted to perform gaming action in real time. Now we can see that there are different broad applications of SOCs that have been listed. So we have seen what is the system on a chip and what is the necessity of having an IP core based system on a chip. And we have also seen the applications of the system on a chip, and then we should see how do we develop as an SOC. Let us spend some time in understanding the SOC design process, which is a system on a chip design process. The SOC design process, we have to choose with required hard cores inside. Then we have to add required soft cores, and we have to add user logic, and that completes the system on a chip design. What is very important for us is to understand is that what is a hard core, what is a hard processor core that is available there inside the SOC FPGA. We also need to understand about the soft processor core, which is what is present, because when we say it is an embedded system, that embedded system can be developed using the hard processor. That means we can say embedded system using the hard processor. We can also say embedded systems using the soft core processor, like NIAS2. In our discussion, we are going to see the embedded systems that are created by using the soft core processor as well as the hard core processor. We are going to understand them in detail. And also what is very important for us is we need to add specific user logic that is important for us. Because after adding the required hard cores and soft cores, we need to add specific user logic that is required, and then we should complete the SOC design process. Now, in order to attain this step, we need to get introduced to what is an SOC FPGA, what are hard processor cores in SOC FPGA, and what are soft core processor cores in SOC FPGA, and why do we need to use FPGAs for embedded system design. So if we get the answers for all these questions, then it would be easy for us to understand the embedded system, and we can start communicating between the processor and the FPGA. To get a clear picture of the understanding behind the system on chip, let us explore what is the need for an SOC FPGA, which is called as a programmable system on a chip or a system on a programmable chip era. Earlier, it was called as a system on a board. Now we are migrating from system on board to system on a chip. So what is the problem statement we have? Is we have to reduce the cost, we have to reduce the complexity, and then we should reduce power. Earlier, you can see from the diagram, you have a separate FPGA chip, we have a separate CPU, And then you have a flash memory, you have SDRAM, you also have a separate digital signal processor, and then you have IOs. As discussed in the first class, we knew that the FPGA also has the basic resources, memory resources. Also, it has the DSP resources, in which we have a multiplier and an accumulate unit, which is useful for performing high-speed digital signal processing application. As we have seen, there is an 18 cross 18 multipliers, then 9 cross 9 9-bit multipliers that are available in Max 10 and Cyclone 5 devices. But now what do we want is, we wanted to reduce the cost, we need to reduce the complexity, and we should reduce the power. Then what is the exact change we expect when we say? We wanted to replace the external devices with the programmable logic. How do we do this when you say? We wanted the CPU that should be present inside the FPGA. The FPGA chip has the processor immersed inside it. And we want all the input-output functions that goes inside the FPGA. Now what we can see here is the CPU is present inside the FPGA, and you have the IOs that are present inside the FPGA, and we wanted this specific SoC FPGA which should handle high-speed digital signal processing applications also. So that means you can see that the DSP also goes inside. Now, what is the kind of thing which we can see is, it was a system on a board era. Now it just changed into a system on a chip. That is called as a programmable system on a chip, we said. So what is the specific solution we got here is, we replace the external devices with the programmable logic. Now, the term what is coined is called as a system on a programmable chip, or a programmable system on a chip. That's what is coined. Now, but now we call this as an SoC FPGA. So for the past 3-4 days, we were discussing about the FPGAs, Intel FPGAs. Today, our focus would be on the Intel SoC FPGA. Now we need to understand what is an Intel SoC FPGA. Let us go through the steps one by one and understand and digest what is the need for an SoC FPGA, and what are the different set of applications that could be targeted, and how do we complete the hardware and software design flow, and what kind of target applications that we can use it with the use of Intel SoC FPGAs. Let us explore them one by one. Let us start with the definition. SoC FPGA devices integrate both the processor and FPGA architectures into a single device. Now, when you say it is an SoC FPGA, it has both the processor and FPGA. So processor plus FPGA is equal to an SoC FPGA. So why do we need to do this? When you say integrating the high-level management functionality of processors and the stringent real-time operations, because we wanted to perform real-time operations, number one. We wanted to perform extreme data processing or interface functions of an FPGA into a single device. So when we wanted to put that, then it forms an even more powerful embedded computing platform. What we wanted is, we want a powerful embedded computing platform. In order to achieve the embedded computing, that is the computing platform, what is required is, it has to perform real-time operations, number one. We require extreme data processing. That is very important for us. And we require interface functions, because already you have the FPGA inside the same chip. So when we have FPGA plus the processor in the same chip, it helps us to perform any complex embedded system design. Okay, what are the other advantages if you get if you have the processor and the FPGA in the same chip? Consequently, they provide higher integration. It is very important, and we have lower power. This is what is the target which we were thinking when we wanted to migrate from system on a board to system on a chip. So what we wanted is they provide higher integration, lower power, smaller board size, and higher bandwidth communication between the processor and FPGA. We wanted to perform higher bandwidth communication between the processor and FPGA. Not only that, okay, what other things will also be present in an SoC FPGA that we need to understand. They also include a rich set of peripherals. That means you have multiple high speed and low speed peripherals which are available there. And you have an on-chip memory, an FPGA style logic array, and high speed transceivers. Everything will be there. Because on the FPGA side, you will have hardcore IPs, hard IPs. Exactly similar to that, you will also have the hard processor which are present in the SoC. Right. So what is the need for an SoC FPGA and what are the features that we have seen in this slide? Now let us move little further and understand what are the hard processors that are present in the SoC FPGA. What is the meaning of the soft core processor? That's what we need to highlight and understand. That will give you a clear idea, right, to understand how do we create or how do we develop an embedded system design using Intel FPGAs. Let us explore a little further. The hard processors is the one which we have seen in the slide. What is the meaning of the word hard? Let us understand, and then we will also see how do we generate that with a soft core processor and complete the hardware and the software design flow. Processors in SoC FPGAs can be hard or soft. Hard processors are implemented in the fixed silicon logic of the SoC FPGA, similar to the serial transceivers. How do you have transceivers as an IP? Similarly, you will have the processors are also implemented in the fixed silicon logic. On SoC FPGAs, however, the processor is surrounded by programmable logic. That means you will have the FPGA section, and that you can use it for custom or application specific functions. So that means you can make a communication between the hard processor system HPS and the FPGA. How that could be possible, let us see that in detail with different reference design examples, which is called as the golden system reference design. The hard processors offer higher CPU performance than soft processors. This is the one which we need to appreciate and understand. Because since there is a dedicated fabric, right, that is immersed inside the FPGA, they always offer higher CPU performance than the soft core processors, which is the NIAS 2. And what are the factors that decide the CPU performance when we say the processor architecture, the clock rate, and the process technology, right? That decides what is the kind of CPU performance. To give you a simple highlight, if it is our low-end SoC FPGAs like Cyclone 5, we have a dual-core ARM Cortex A9, whereas our Stratix and Agilex devices, our 14 nanometer and our 10 nanometer device, has a quad-core application processor A53. So there is a difference in the architecture. Here it is like 32-bit, there it is 64-bit. There is a fundamental difference in the architecture. What kind of ARM processors are embedded inside the fabric when we say there is a fundamental difference. Based on that differences, there would be a change in the processor architecture. That means the clock rate and the process technology. There would be an impact on the CPU performance also. Okay, now what is the meaning of the hard that we have understood? But what is its position inside the chip? That's what we need to see. As the name implies, hard processor feature sets are fixed and typically offered only as a variation of the particular SoC. Now we can see the number and type of the hard processors within an SoC FPGA are also fixed as a function of that particular SoC FPGA. That means the position of the hardcore processor is fixed inside the chip. Okay, now what are the different set of SoC FPGAs we have? It also includes Agilex, our Agilex device, which is our 10 nanometer. And you can take our Intel Stratix 10 SoC FPGA, Intel Aria 10 SoC FPGA. Then you have Aria 5 SoC FPGA, and also we have a Cyclone 5 SoC FPGA. So what is missed in this discussion is we started with the Max 10 devices, the DE10 light board. So the Max 10 device is having only the soft core processor, which is NIAS 2. It is not having any hard core processor. So today we are going to build an embedded system using the Max 10 device. We are going to build an embedded system using the NIAS 2 soft core processor. That we will see how that could be possible with the help of a demo. And the second thing what we can also appreciate and understand is using the Cyclone 5 device. We can generate an embedded system design using Cyclone 5 and ARM. That is hard processor based embedded system. Right. Let us explore and understand the details right now. So what is the takeaway? Key takeaway here is that hard processors offer higher CPU performance than soft core processors. That is one key takeaway. We have to note it down. And the hard processors are implemented in the fixed silicon logic of the SoC FPGA. Let us move on to the soft processors. So till now we were discussing about the hard processors. Now let us start with what is the soft processor which is present inside the Intel FPGA. Now when you say Intel FPGAs, it is also present in all Intel FPGAs as well as Intel SoC FPGAs, right? So soft processors such as the NIAS 2 processor are implemented in programmable logic using the on-chip resources such as logic elements, multipliers, and memory, and it can be instantiated in almost any FPGA family. That means what is the meaning of the soft core processor? When you say the NIAS 2 soft core processor is going to take the resources which are present inside the FPGA. So we can see that how many resources it has taken in terms of lookup tables, in terms of memory, in terms of DSP resources that we can take. That we can definitely look into. The performance and the cost of a soft processor depends mainly on the FPGA, what we try to do. So that means the performance and the cost are typically lower than in hardcore processor. That means it is not a dedicated fabric which is immersed inside the FPGA. Since it is going to use the FPGA resources, the performance and the cost are typically lower than in hardcore processor. Then we will have some multiple questions which we have, like for what kind of applications we could use NIAS 2 and what is the fundamental difference like that. So I will show you our Intel page and you will get more answers about that. Let me walk you through that to get a better idea after explaining the next slide. The number of soft processors that can be instantiated in a single device is limited only by the device resources. That means it is logic and memory. Now, what is very important point which we also need to note down, the high density FPGAs, right? So that means you have a Stratix 10 and then you have Agilex devices can contain hundreds of soft processors. That means you can see how many NIAS processors can be inside like that. So it can have different soft processors that could be implemented like 16 or 32-bit. And it can also be for performance optimized or logic area optimized and so on. So performance optimized, the number of resources will be different. It will show different set of lookup tables, different set of memories and then DSP resources. When we target it for logic area optimization, optimized for area, that is different. Optimized for performance, that is different. There would be a change in the resources. All right. Next important thing what we also need to understand is you can choose to migrate your soft processor based designs to hard processor based. So today we don't have any set of applications to work on, let us assume. But tomorrow you are thinking that, okay, I wanted to migrate my soft processor based embedded system design. For example, you take from Max 10 to Cyclone 5. You wanted to migrate to the hard processor design. Then you can see that how it was used in the soft processor based embedded system design, and what is the necessity of migrating that to the hardcore processor, right? So for example, if you can see that, okay, there is a link that is provided which directly take you to the NIAS2 processor, right? So you can see the programmable processor projects. That means you can see that what kind of information that is provided to you, right? And now you can also see if that doesn't work out, we can also try parallelly. Okay, there is a problem in the page. Let us try from here. Intel IP course. Let us start from there. It will take you to FPGA IP, that is Intel IP course. Okay, so it reaches the page like Intel FPGA IP portfolio. Now, you can see on the resources, like you can see the IP product portfolio. You can see the NIAS2 soft core processor is listed. So when we expand that, we can see the details of the NIAS2 soft core processor is explained here. You can see the NIAS soft core processors are designed specifically for Intel FPGAs. And we can also see the soft processor series is suitable for wide range of embedded computing applications, from digital signal processing system control. Any kind of digital signal processing applications or any system control applications, we can target the NIAS soft processor series. That is all. We also have a NIAS5 processors, which is based on the open source RISC-V instruction set architecture. But they are available only in the Quartus Prime Pro edition, which is from 21.3. Since it is available only in the Pro edition, we are not covering that in our workshop because we wanted to discuss more on the Lite edition. So the NIAS2 processors, which it is available on the right-hand side, is our focus. You can definitely look into the features of NIAS5 processors. There are multiple documents and there are multiple videos that are available related to NIAS5 processors. The moment we click the NIAS2 processors here, they are versatile and they deliver the flexibility for your cost-sensitive, real-time, and safety critical applications, right? So in such cases, we can definitely go for NIAS2 processors. And there are two more important things I need to show it to you before we get into the session slides again. What are the things that we need to look into here is, as I mentioned, that you can use it for optimized for area, as well as you can optimize it for the performance like the type. So when we look into the details, you can see the NIAS2. It is having a fast variant as well as you have an economy variant. When there is a fast variant, Intel specifically designed the fast processor for high performance. That means you wanted the high performance. Also, you need to check here the economy processors to use the fewest FPGA logic and memory resources. So as explained in the slide, it is like you can optimize it for area. You can also optimize it for performance. That means when we open the NIAS2 processor in the IP catalog, it will ask us that whether you wanted to use the fast version or you wanted to use the economy version. So that information we can definitely get into. Now, what are the other questions that need to be answered here? Okay, while creating an embedded system using the Intel FPGAs, what kind of specific targeted applications, what we can get, what are the best benefits you can see? So there are multiple factors, but then I just wanted to show you what is given in our homepage so that you will get a clear idea like what is the basic scenario behind this. So the first thing is flexibility. Then you have a long life cycle. It is low cost because you don't need to invest any amount for a dedicated hardcore processor because it is going to use the resources which are present inside the FPGA. And now, what is the specific thing which we need to note out is what is the kind of the frequency, the operating frequency that is important for us. So Fmax by device, it is shown in terms of economy and then fast. There is one important thing which we should keep in mind here is like when we compare this with the hardcore processor, right? The hardcore processors will offer higher CPU performance than the softcore processors I explained in the slide. That means you cannot go up to 1.5 gigahertz and all with the NIA softcore processor because those kind of things would be possible with the ARM core processor. But what is important for us is like the kind of applications which we could target for. You could see the kind of applications, right, where you have a power and cost sensitive application. Because this is what we wanted to understand, right? Whenever we learn something, we will ask, okay, what is the kind of application which we could target for? We have a power and cost sensitive application. In that case, it is going to use only the 600 logic elements. You can see a logic element is a classic example, which is a 4 input lookup table plus 1 register. I explained to you the first class, right? Now you can see that with low has 600 logic elements, right? Yes, NIAS 2 processor is a soft core processor. That's what we are discussing. That it is a soft core processor. It is going to use the resources which are present inside the FPGA. Right? So you can see that this is the most widely used soft processor. Right? We are discussing about the NIAS 2 processor because that is also present inside the SoC FPGA along with the hardware. Right. Now you can see it could be targeted for real time and it can also be useful for application processing. But here, there are two important things which we should note down. You cannot use the same variant for the similar kind of applications, right? There are different set of variants required for different set of applications. Here you can see that it is economic core. Here we try to use the fast. And another important thing which we need to get into is like the kind of ecosystem. That means what kind of the IP support and how do we create an embedded IP suite. All those information are available here. Not only that, you will have the NIAS 2 processor documentation and NIAS 2 EDS, which comes along with the Intel Quartus Prime Design software. How to use that NIAS 2 EDS, I will show you a demo today. And we can also see, right, how do we interact with other designs, right? And what are the questions to be answered? Like, why do you want an NIAS 2 processor based embedded system design? And what is the advantage or how do you compare that with the hard processor based embedded system design is the set of questions which we will have in our mind. To solve that, okay, there are some set of questions with answers I just wanted to show you in our homepage so that you can refer that later in detail. I don't want to cover everything inside the presentation slide. Let us go through that in detail here. What is the NIAS 2 family of embedded processor when you say it is a 32-bit RISC processor that is available? And how many processor cores that make up when you say, you can see, as I mentioned, there are three things. That is, one is the fast and other one is the economic. Right? We don't use much on the standard versions right now. And what are the benefits of using a soft processor over a hard macro? So this is the kind of question we will definitely get every time. So when it is a soft processor, it is available as a HDL. That means by implementing a processor as an HDL coded intellectual property core, you get an exact fit solution because you can choose the peripheral, performance, and the processor mix best suits your system needs because there is no specific location for it inside the FPGA. Whereas when it is a hardcore processor, it is fixed. Whereas when it is a soft core processor, it is flexible. And you can see on the other side, the hard macro implementation are essentially ASICs and do not have the same flexibility, right? And very important thing is it can get migrated to any Intel FPGA and the SoC FPGAs because all the FPGAs. Almost all FPGA families have the soft core processor. That means you can see that here. Soft core processors, on the other hand, can migrate immediately to the latest technologies such as Stratix or Cyclone, or we can also take it to the ARIA 10, which is a mid-range FPGAs. That is the greatest advantage. I hope this question would be asked, right? So you will have many questions, and then there are answers available here. I just wanted to let you know, right, where these informations are available. So please go through that, because these questions and answers will provide you more information about it. And one more important thing which I can show you is like which Altera FPGA families, right, like Intel FPGAs at this junction, support the NIAS2 processors. When you say all SoC FPGAs and all FPGAs, right, have the family support, there is no worry. Right? That is not the case with the SoC FPGAs, right? So go through this, and you can get more information about it. So what I can do, I'll just paste that in the chat window, and I request everyone to just go through that in detail. Okay, right. Let me again go through any other questions are there in the chat. Right. So there are multiple things that are happening with respect to the NIAS 2 and NIAS 5. I can provide more details about the home page that will have more information about the firmware development also. Right. I will share that information with you. Right. Now let us move on to the presentation again, and we explore the details. So let us start with the soft processors, and we will move on to the next thing. Right, we stopped here. Let us continue from this place. Now, the question to be answered is, how do we perform an embedded system design using an Intel FPGA as well as the Intel SoC FPGA? FPGA based embedded system design, when we say, the question is, why do you want to create an embedded system design using FPGAs or Intel SoC FPGAs? How do we solve this problem? And what is the need? Let us explore them one by one. The first thing is, we wanted to use FPGAs in an embedded system. The first question is, what are the kind of use cases? Like typical uses include what? Right, I showed you about what are the applications of the NIAS2 processor. Now let us comment on what are the typical uses of FPGAs for embedded system design. The first thing, if you go through, it shows I/O and peripheral expansion. Now we can add peripherals missing from your current processor, such as LCD or memory controllers, or increase the number of I/O channels in your system by adding Ethernet, general purpose I/O or UART ports. So the first advantage is like we can expand I/O and peripheral expansion. The second thing is called co-processing. So this is one important application where we use the FPGAs for embedded system design. Right. So if you go through the bullets, you can get a clear idea like what kind of applications that could be targeted for. We boost system performance by moving compute intensive algorithms from software running on a processor to hardware in the FPGA. So in that case, we wanted to use the FPGA as a co-processor. Signal processing, image processing, and packet processing applications achieve orders of magnitude performance improvement running in hardware rather than software. So in most of the applications of signal processing, image processing, and packet processing applications, we wanted to have performance improvement. So that could be possible with the help of FPGA-based embedded system design. And the third one is custom embedded control. In this case, we can decide, you decide which and how many processors like peripherals, interfaces, direct memory access channels, and memories to include in your custom embedded control. So we can see what kind of processors and how many are available. And you can perform the interconnection and integrate that into an embedded system design. And the last option is called as the multiprocessor, which is very essential and important for us to understand. We have to accelerate our software development, and we wanted to improve the code reliability, and we need to increase the maintainability by distributing the tasks across several CPUs. So in that case, we can design a multiprocessor system as a custom system inside the single FPGA to augment an external CPU or a digital signal processor. So you don't want to have an external CPU, or you don't want to use an external digital signal processor, because you have the digital signal processing elements that are available inside the FPGA itself. I hope there was a question in the chat. Let me know what is that. Right. So, So can you tell us how? Right. So that's what I explained, right? So the idea is, when you are trying to use an image processing algorithm or a signal processing algorithm, what we wanted is, like, what would be definitely there in that case is a kind of multiplications, right? So the multiplier and accumulate units which are involved, that could be taken to the FPGA, because you have specific digital signal processing resources that are present inside the FPGA. A multiplier and accumulate unit which can provide you the kind of parallelism, right? So that is not available in the processor. So you can take that kind of computations, and that can be performed in the FPGA, and then the remaining things you can do that in the software. That means it is better to do those kind of algorithms where we have signal processing, image, and packet processing, where most of the things would be in terms of matrix multiplications or multiplier and accumulator unit applications. Okay, that's the base idea. Right, let us move on to the next principle. What are the system level benefits of integration? Now the question is, whenever we take a specific scenario like this, right? You have a processor separately, and then you have the FPGA separately, but then now we need to integrate it. Okay, so at the end of the day, what is the kind of advantage what we get? That's what we need to understand here. When you say, before, you have devices that are connected to the FPGA, and then you need to connect to the memory, and then we have CPU that is separately connected. But now what happens is, when you perform the system level integration here, we have FPGA plus CPU both, right? So then you can see that device, and then memory you can see. Now, what are the 4 important bullets that we need to understand and get highlighted here is, first thing is, we have increased system performance. That's the first bullet, you can see that. And the second one is reduced power consumption, because when I started the sessions with applications of SOC, I explained you that what kind of applications they are targeted for and what are the characteristics. If you just relate them, what we want is increased system performance. Yes, that is getting achieved in an SOC applications. Then reduced power consumption. We have seen the example of a mobile phone, cell phone, where you wanted the operate at a very low levels, right? So reduced power consumption, reduced board size, because we are not interested to have a mobile phone of brick size, right? Now, what is the size of the mobile phone which we have, that we can easily understand now? So we don't want that the term of system on a board. We wanted to the terminology of a system on a chip. So now we can see that what is the size of the mobile phone, right? What was the size of the mobile phone 20 years back, and what is the size right now? And how compact is it? And then what is the kind of SOC applications that are targeted, we can see now. And we can see it is a reduced board size and reduced system cost. Now, the 4 bullets which are required, all those things were met when we bring processor and FPGA together into a chip. Now, let us easily understand the definition now. We are going to get the best of both worlds. So the SOC FPGAs provides the best of both worlds. That's what we see here. You have a dual core ARM Cortex A9 MP core processor. You have an hard memory controller, and then you have the SoC FPGA. So ARM plus FPGA is equal to SoC. So you have the ARM Cortex A9, dual core ARM Cortex A9 that is embedded. Along with that, you also have the FPGA section. So ARM plus FPGA, we call that as an SoC FPGA. So it doesn't mean that it is only for 28 nanometer FPGA, not like that, right? It is available for, right, the low cost as well as mid range, as well as we have high-end SoC. As you can see in the slide, you have the Cyclone devices, you have the ARIA, which is mid-range device. We have Stratix, and we also have Agilex, right, which is not captured here. We also have Agilex SoC. So ARM Cortex processor plus Intel FPGA provides the entire platform of Intel SoC FPGAs. So to get into the detail where you can get more information about it, right? So I can just walk you through that. You can go to our home page, and you can see, like in the products tab, you can see on the right hand side FPGAs and programmable devices. Here you can click Intel FPGAs, or you can also click here Intel SoC. The moment you take it to the Intel SoC FPGAs, where we can see that Intel Agilex FPGAs and SoC FPGAs and Intel Stratix are here, right? Only when you click the Mac series, you don't have any SoCs. For example, the Intel Cyclone 5 series, you have a Cyclone 5 FPGAs and SoC FPGAs, which we are going to discuss in detail today. Right, as I mentioned, in the Mac series, you have the NIAS 2 soft core processor. We can do an embedded system using it. Right. Okay, fine. So that you can definitely get into it. Okay. So if you go through the Intel IP course, that will provide you the details. So from here you can take. Okay, either you can go through the entire IP portfolio, or you can click this NIAS 2 processor. From there, you can take the details. Okay, so this information may be sufficient for you. Please go through that. All right. All right. Let me continue now. Right. So in the SoC page, what is important for us to note down is you can click this Intel Agilex FPGAs and SoC FPGAs, and then you can see what are the different SoC FPGAs that are available. Similarly, you can click Stratix, and you can say Intel Stratix 10 FPGAs and SoC FPGAs. Similarly, you have ARIA, where we have a mid-range SoC FPGAs like Intel ARIA 10 FPGAs and SoC FPGAs. Also, you have ARIA 5 FPGAs and SoC FPGAs. Okay, so you can go through this page, and this will provide you the details of the FPGAs as well as SoC FPGAs. And we also have a book related to the world of FPGAs, FPGAs for Dummies. If you wanted to download, you can download the free ebook. That information is also available here. All right, so let us move on. What is the quick summary? Till now we learned something, but then how do you split it? That's what we wanted to understand. So how do you say that this is FPGA and this is HPS, that is a hard processor system, when you say? Now, when we take an SoC FPGA, like the D1 SoC, which we utilized for our LabsLAN setup, right? It is an SoC FPGA. But then what is present on the FPGA side and what is present on the HPS side, and how are we going to make communication between them is the thing which we need to understand. On the FPGA side, it looks like an FPGA. It works like an FPGA. Standard FPGA development flow, standard FPGA development tools, And we have Intel Quartus Prime design software. That means we are going to use that platform designer system console. So platform designer has been explained to you. System console we are going to discuss today in detail. So on the FPGA side, we are going to use all the FPGA system development tools. Let us see on the right hand side. When it is an ARM Cortex hard processor system, it looks like an ARM processor system. It works like an ARM processor system. And we are going to use the typical ARM processor development flow and typical ARM processor development tools, crash compilers, debuggers, data, program trace tools, etc. So here, I'm going to show you the kind of debugging mechanisms where we are going to use the signal tap logic analyzer as well as the system console in order to debug the embedded systems with respect to SoC FPGAs. Now let us compare the key features. Now when it is a processor, you have a dual core ARM Cortex A9 that is available in Cyclone 5, ARIA 5 and ARIA 10. And when it is a static stem device, it is a quad core ARM Cortex A53. Now what is important is you have to also understand that that is the same for Agilex also, right? Even though it is covered only this here, we have to understand that is for the high-end FPGA. So I have just captured static stem to compare that's a low end with the high end. So you have a processor performance where you can see it can operate up to 1.5 gigahertz. That is not the case when it is the logic with respect to NIAS 2 processor. I will show that when we discuss about the NIAS 2 processor based embedded system design. Now the memory controller support, if you see, you can see DDR3, you can see 400 megahertz and 533 megahertz, 1066 megahertz and 1200 megahertz. Now we can also see the logic density. This is very important for us. Like how big is our FPGA? That's what our next question is, right? So whenever we design a complex system, the logic what comes in our mind is what are the resources that are present inside the FPGA and what resources are used by your design? How much area is consumed and how much area is left out, right? And what other features we can add to the design? All those informations we need to understand. For that, we should know how much density is the FPGA. So for example, if you go through the Cyclone 5, we have 25 to 110 daily logic elements, kilo logic elements, and then you can also see here it is million. So you can see 5.5 million logic. Now you could also see the transceiver speed where we can go up to 28 Gbps in terms of static state. Right. So this is on the Intel FPGA side, and then let us compare what is present in terms of Cyclone 5 as well as with the static state and Agilex devices. Right. Now let us compare. Earlier we have seen the Intel FPGA portfolio. But in this slide, we are discussing about the Intel SoC FPGA portfolio. The Intel SoC FPGA portfolio, if we say that, right, so let me see what is the question. Right, so it's a good question. So there is a different set of, there is an HPS clock as well as there is an FPGA clock, right? So we are going to set it. So what we are going to use the clocks on the processor side, and then what is the clock that is derived from the PLL on the FPGA side. So those informations are required. And based on that, we are going to synchronize them, right? Because it is definitely that the peripherals and the devices which are present on the FPGA as well as on the processor side will work with different frequency. But what is very important is when we create an embedded system, we have to see what is the FPGA clock and what is the HPS clock and how are we going to synchronize them, because there may be an SDRAM involved, there may be different set of devices involved or the peripherals involved, where we may need to do some kind of clock domain crossing techniques, or we wanted to insert dual port RAM, which can work as a FIFO in order to synchronize. So there are so many techniques, right? But at this junction, yes, definitely, yes, there are different synchronization mechanisms that are available, and that we can do that when we configure the system in the platform design. So the Intel SoC FPGA portfolio, if we say, we have a Cyclone 5, which uses the 925 megahertz dual core ARM Cortex A9 processor. And then you have the ARIA 5, and you have ARIA 10, Stratix 10, and Agilex. I wanted to bring everything into a single slide so that you get a clear picture of, okay, what resources are available in terms of memory, in terms of DSP, and in terms of FPGA side, and also on the ARM side. Now, all these SoC FPGAs, you have hardcore processor. That means you have a dual core ARM Cortex A9, which is embedded inside the fabric. And I have also listed about the FPGA resources here, right? You have the multiplier, you can see that. How it is listed, you can see the DSP resources, the basic resources, the memory resources, and then the processor. You can also see there is a transceiver. So in this fashion, if you go through, what are the two important highlights I can show you? Number one, you can see the different set of multipliers that are available. When you take Cyclone 5 device, we have up to 224 multipliers. Whereas when you compare that with ARIA 5 or with ARIA 10, you can see, which is a mid-range FPGA or mid-range SoC, we have 3,356 multipliers, which is 18 cross 19. The same 18 cross 19 multiplier, we have 11,520 multipliers in Stratix 10. And then you can see there are 17,056 multipliers in the Agilex devices, which is based on the 10 nanometer super FinFET technology. Now, if you see here, 17,056, when you say, so 17,056 into 18 cross 19 multiplication, that could be possible. That is the density of the FPGA. Now, when you compare Agilex with the Cyclone device, you can see there are up to 224 multipliers. Here you can see 17,056 multipliers. How much is the density of the FPGA? That we can easily compare right now. Now let us go through the Cyclone 5 SoC system architecture, where you have a hard processor system, HPS, and then you have an FPGA. Now you can see this is the FPGA section, and this is your HPS section. The blue one is the HPS section, which is the hard processor system. That's what we call. So in the hard processor system, you have a dual core ARM Cortex A9 along with the neon floating point unit. Now you can see there are peripherals that are present on the HPS side, and you also have the FPGA section where it is based on the 28 nanometer low power process. You have an 8 input adaptive logic module, 8 input ALF, and you have a variable precision DSP, M10K memory, and 640-bit MLAPS. M10K memory, when you say, as I mentioned earlier, in the Max 10 device, you have M9K memory, whereas in the Cyclone 5 devices, you have an M10K memory. So that means it is 10 into 1024. And we also have 640-bit MLABs, that stands for Memory Logic Array Block, in which the memory is constructed by logic array block, which is called as a distributed memory. Now, on the communication side, if you see, how are we going to communicate between the HPS and the FPGA? If you see, we have HPS to FPGA. Also, we have FPGA to HPS. Hard processor system to FPGA and FPGA to HPS. Both are available. And how are we going to interface between them? And how are we going to perform communication between them? If you say, we have high bandwidth on-chip interfaces, which allows us to perform HPS to FPGA as well as FPGA to HPS interface. Also, we can say FPGA to SDRAM interface, which we discussed during the lab yesterday. Now, that is for the Cyclone 5, and this is for the Stratix 10 SoC FPGAs. There is a fundamental difference, as I mentioned. In the Cyclone 5 and ARIA 5 SoC FPGAs, we have a dual core ARM Cortex A9 as the hard processor core, whereas the hard processor system of Intel Stratix 10 and Agilex devices uses a quad core application processor A53. That means you can see there are 4 cores, and then you can see the free. Now it is based on quad core ARM Cortex A53 processor, and it is based on 64-bit, right, ARM V8 version 8 architecture. And on the FPGA side, there is no much change. It is exactly same like the earlier one, but then there are differences in terms of memory, because in the earlier case we used M9K and M10K, but in the statics devices we have M20K, right? So each block RAM would be of M20K, so M20 into 1024. You have 8 input adaptive logic modules. You will have variable precision DSP blocks and hard IP for PCI Express. All these informations are available. That is on the FPGA side. Right. Now the question is, okay, I need to start somewhere. How do we start? Let us start that. How do we start getting into the design? So even though we are going to focus on the Cyclone 5 device and Max 10 devices, but I will provide multiple details because this will be helpful for you to get into the high-end SoC FPGAs which are available right now. We have Stratix 10 SoC FPGA, and also we have an Agilex SoC FPGA. So where we can start, when you say there is a golden system reference design that is available, right? I will share the links with you, where you can see how we can communicate between the FPGA fabric as well as the hard processor system. It means in this diagram, you can see what are the peripherals that are present in the hard processor system, that is on the HPS side. And also we can see that what are the processor, that means what are the things, the peripherals that are present on the HPS side, FPGA side as well as the HPS. Here you can see it shows the FPGA fabric, and here you have the hard processor system, which is on the HPS side. What peripherals are there? And you can see that the interconnections are given here. HPS to FPGA. So this is the master, and you can see slave. So M, S. And here you can see again master, then slave. And again you can see FPGA to HPS, slave, then master. How they are getting interconnected, that information is also provided. And who is the master and who is the slave, and how the interconnection is based, right, or connected between the master and the slave, that information is provided here. And since it is an FPGA, on the FPGA side, you will have some resources. That means you are aware that on the FPGA side, you will have switches, LEDs, push buttons, etc. Right? So that is specified here. You can see SysID, LED PIO, button PIO, dip switch, right? All these things are slave devices which are present on the FPGA side. Now, what we can do through the hard processor system, you can control the resources which are present on the FPGA, like HPS to FPGA. You can communicate like that. What kind of SoC applications we wanted to do, we can try to do like that. So I can show you where are those reference designs, and then we can get into one or two. I can show demos today, and the remaining you can also practice. I will share the entire details with you. And how to access the documentation resources. So the moment we enter into our product page, that's what I showed you. On the right hand side, you can see support. The moment you click support, and it can take you to get started, where you will have technical documentation, videos, training courses, and that are targeted for the Intel Stratix 10 FPGAs. Because we targeted it for the Intel Stratix 10, automatically you can do it. You can also do it for Max 10, you can also do it for Cyclone 5, you can also do it for Agilex devices. So you can search for the device in the family in your favorite search engine, and you can click first result, and automatically you can get started. And there are direct links that are supported, provided for Stratix and Agilex devices, which I can share it with you while sharing the presentation. Now, this slide will give you a clear picture, because in the earlier slide, I didn't capture the entire logic. Now you can see on the right-hand side what is available and how do we compare and contrast between the HPS and the FPGA, and how do we make communication between them. So the diagram shows the peripherals which are present in the HPS as well as soft peripherals in the FPGA that are enabled by the Golden System Reference Design, which is called GSRD. And this GSRD is meant to give you a good starting place for your own design. We don't want to create our design from scratch. We can just go through the Golden System Reference Design and then we can customize our design to suit the kind of applications what we wanted. And whenever we enable a new peripheral, it involves configuring the component differently and modify the device. Whenever you add it, automatically it will change the device. Now you can see that these are the information that are present in the hard processor system HPS side. And you can see these are the information that are provided on the FPGA side, and we can make communication between them. Here you can see FPGA to HPS to FPGA, and then you can see lightweight HPS to FPGA and FPGA to HPS, which is slave and master. Right, so let me just walk you through one more important thing to just compare, like what is present in the Cyclone 5 we have seen and what is present on the static side. Now, when you go through the HPS, the hard processor system in the Cyclone 5 device, right, you can see it is like 25 KLE. Whereas there, if you see, right, it takes like 2.8 billion logic elements. Now, you can see that this is the FPGA section and this is the HPS section. Now, you can see that the HPS can take the larger portion of a device in the Cyclone 5 device, but the same HPS takes the small portion of a device which is static extent. That means you can easily imagine what would be the density of this FPGA, right? Now, when we are comparing, right, so I showed you about the Cyclone 5. In this slide, I'm just comparing about the ARIA 10 and the static extent. What is the necessity is like from a mid-range SoC FPGA, we are migrating that to the high-end FPGAs. Then what are the things that need to be kept in mind? There are two important things. One is you have a dual core. That means it has a ARM Cortex A9, whereas here it uses a quad core. And another important thing what we need to note down here is the FPGA to HPS bridge operate at 32, 64 or 128 bits, whereas here it is 128 bits that is fixed. And FPGA to SDRAM ports, if you see, we have 232, means it can have 64 or 128 or 180 bit you have. But here you have 128 bits that is available. Now let us explore the HPS system with a small example, targeting it for the Cyclone 5 device and then understand how the communication happens. Okay. So to do that, let us see that, okay, this is based on the ARM Cortex A9 and this is based on the ARM Cortex A50. There is a fundamental difference between our Cyclone 5 as well as the static devices. Right? We don't want to get into much details, just understand that how they are different, because here we have dual core, here we have quad core, and this is 32-bit address size, and then you have a 64. Other informations we can refer into it, and we can develop the embedded system appropriately. Right? Let me just take you through the logic here. Just a simple example, developing an SoC FPGA design. I will just show you a demo, and then we will enter into the embedded system using NIAS. And then we can also debug the system. Right, so let us open the Cortex Prime design software. So in the new project wizard, we can see here like SoC design. And say Cyclone 5. Right, what is the name of the project? Something you can give top. The project. Next. And here you can see Cyclone 5. Okay. Now, what is important here is when you are selecting the Cyclone 5 device, how do you know that it is an SoC? That's what you can see here. It is SX or AC. S stands for SoC. The device what you are selecting should be an SoC device. Only then it is easy for us to perform that, right? For example, if I say here, name filter, IC5C, SEMA, something like that, I type. Now we need to see, right, whether this is an SoC device or not. That means I can see that these are the different devices it shows, right? Which device is the SOC device? I need to know that. So without knowing whether it is an SOC device or not, I cannot go into the details. So now you can see that. Okay. What are the memory PCI hard blocks, memory controller, DSP blocks, DLL? Here you can see that there is an HPS CPU core, right? When you expand it, you can see that. Now, the moment you type family, and you can see there are multiple devices. Let me just select something, right? You can select anything at this junction, but while creating the project and targeting it for the corresponding device, then you have to select the corresponding family filter. This is just a demo example. I'm just selecting something for you, but the idea is like what is very important for us to note down here is along with the available devices, right? When you drag and see the details here, along with the PCIe hard IP blocks, memory controllers, memory bits, DSP blocks, you can also see there is a HPS CPU. We have to see this option. That means the device what we have typed here is an SOC FPGA. If this HPS CPU cores is 0, that means you are targeting a device which is not an SOC family. It can be either GX or GT, which is only an FPGA, it is not an SOC FPGA. We have to be very, very careful with that, right? Some devices are only FPGAs. We have to be very careful whether are you selecting the corresponding SOC FPGA device. Okay, now once we say that yes, next, EDA tool settings, and you can come to the summary. You can see that I have selected the Cyclone 5 device. And we can move. Now, if you go to tools, right, and then see here we need to go to the platform design. There is a fundamental difference in the platform designer what we opened earlier, because the platform designer what we opened earlier is based on the NIAS2 device, right? It is just a specific soft core processor. But now what we are going to do is we are going to bring the hardcore processor based embedded system design. Okay, so now when you maximize this, you can see there is a clock and reset. But then here what we can type is we can type hard processor system. The moment you type hard processor, right, we can see, or you can also say HPS, the easiest way to search. The moment you type HPS, you can see that hard processor systems, it shows that ARIA10 hard processor system is inactive and the Stratix 10 hard processor system is inactive. But what is active here is ARIA5 or Cyclone 5 hard processor system, because the family in the family filter what we targeted is for the Cyclone 5. Just click that. Okay. Now, the moment you open the HPS, the hard processor system, you can see on the left hand side, it shows the clock and the master, right? The master and slave. But what is important for us to note down here, you can see H to F. That means it is HPS to FPGA. And if it is F to H, it is FPGA to HPS. You can see axis clock, right? And axis slave. And you can also see the reset master, axis master. That here also you can see HPS to FPGA. And then you can also see FPGA to HPS. Okay, and it also shows HPS underscore 0, which is nothing but your ARM processor system. Right. And now what are the important informations which we need to go through is there is an axis bridge, which shows that FPGA to HPS interface width, and you can also see, right, what are the DMA peripheral requests and all this information are available here, right? And you can also see on the right hand side, right, you can see there is an SDRAM, and also you have a HPS clock. You can click that, where you can see what is the external clock sources, and FPGA to HPS PLL reference clocks, and peripheral FPGA clocks. All those clock informations you can see. And also if you click SDRAM, you wanted to use what kind of protocol that can be selected. Either it can be DDR3, or it can be DDR2, or it can be LPDDR. Whichever you want, that can be selected appropriately. Right, so let us just check because we are not going to change any settings here. Just we'll understand. Now what we wanted to do is, you can see there are multiple errors. Let us just rectify them, and then we will just add only one peripheral and close the system. Right, this is just a small example. Now we wanted to add an on-chip memory here. So just take the RAM or ROM. And this can be, again, you wanted a dual port access. Yes, you can say a dual port access. Otherwise, you can just keep it as a single clock operation, but it is a single port RAM. So there are two parts. One, you wanted to initialize the content of the memory. Then you can initialize the memory content. For that, we need to upload the memory initialization file. If we say that we don't want to initialize the memory content, we can just say. Now you can see that it shows multiple errors where we need to connect the clock, we need to connect the reset, etc. Now you can see that. Okay, so we need to connect the clock. You can click the open dot. You can connect the reset. You can also connect the Avalon memory mapped slave to the AXI master. Now you can see there is a fundamental difference because it is based on the AXI, right? It is based on the ARM core. So therefore, the slave device, which is our Avalon memory mapped slave, which is present on the FPGA side, we need to connect to the master, which is the AXI master. You can see that AXI interconnect. You can connect that. You can see HPS to FPGA, lightweight AXI master, and you can also see HPS to FPGA AXI master. So we connect that to the advanced extensible interface. Right now, we also need to connect the clock and reset for the card processor system. You can see there are multiple errors here. The SDRAM clock need to be connected to the clock. So you can just see here HPS to FPGA. So you can just see here which information is provided that we need to connect it. So the F2H SDRAM clock need to be connected. And you also need to connect the AXI clock. Okay, so that clock information are done. We also need to connect the F2H AXI clock that need to be connected. And also you need to connect the lightweight AXI clock. So now you can see that also everything is connected right now. Now what you can do is you can generate the HDL. So you complete the system. While generating, you know that we will get the synthesized files as well as the simulation files. We generate that and say save. And you can just save the test.qsys and say save. Close. So it will generate the system and then it will show if there are any warnings, right? Because in our case, there are no errors, right? But then there are some warnings that are available. It shows that, okay, generated but completed with warnings. We can close it. Now what we can do is, like, we have the platform designer ready. We can go to project and then we can say add or remove files from the project, and then we can add the test.qsys which we generated and to the Quartus Prime Design software. Go to files and you can see the test.qsys is added. Right. So let us get into the details of creating a large design later. But this is just to give you an overview how that could be taken into account. Right, now let us move on to the next topic. And after creating the embedded system design using the NIOS, right, soft core processor, we will again come back and then develop a specific example using the hard processor system. Right, how do we do that when you say? We have to open the design by using the corresponding QPF, which will be available there. There would be a Quartus project file. And after getting that Quartus project file, we need to perform the platform designer, and then we should continue all the operations in the platform designer, then take it back again to the Intel Quartus Prime design software, perform compilation, and ensure that the process has been done. So this is the way we are going to do it. To do that, what is required is we already knew platform designer because that is the common tool that is used for the NIOS 2 soft core processor based embedded system design. Also, we are going to use the same tool for the hard core processor based embedded system design. So it is a GUI based system integration tool for system design. And the main advantage of the platform designer tool is it simplifies the complex system development, and it automatically generates the interconnect among various off-the-shelf and custom IPs. And it provides a platform for IP integration, custom IP authoring, and IP verification. And it also enables the design reuse. Right, so let us start. Okay, how do we start with the HPS component and then do it? So this is what I showed you. But then let us start with a specific example from the golden hardware reference design, and then we will continue the lab demo right now. I will show the steps one by one, and then during the hands-on lab sessions in the afternoon, we will continue the steps and ensure that we are able to complete the SoC design model effectively. Right, what are the informations we have? The Intel statics and hard processor system. We have the manual, and we also have the platform designer training information that are available, which I can send that. Right, so this session ends right now. Now we are going to start with the embedded system design using Cyclone 5 and ARM with a lab. I will explain that to you, and what are the important things that need to be taken care while performing that lab, and how do we understand the informations that are present in the lab document. I will walk you through that step by step, then we will continue with that. I will stop sharing for a minute, and if there are any questions in the chat, I will just address it, and then I will come back immediately with this. All right, so I don't see any questions. Let me start. So we are going to see the lab exercise. I am going to show you a demo. The same would be explained to you during the hands-on lab. I request you to complete that hands-on lab. Using the Intel FPGA Quartus Prime design software with an SoC. That is the lab demo which we are going to see. So what is the flow I'm going to explain to you is like we are going to begin with the golden system reference design model, which is available in our Terasic website. It is also available in the rocketboards.org. I will spend some time and explain you where those reference designs are available and how you can choose them, and which could be targeted for a corresponding FPGA family. I will walk you through that step by step, and then we'll get into the details. So we need to begin with the golden system reference design model, right? And then what is the flow we are going to see? I will explain that right now. We are going to follow the typical design flow, how it is performed in the SoC FPGAs. We are going to create or open Intel Quartus Prime design project. This is what I did. And we need to select the SoC FPGA device. On the left-hand side, if you see, it clearly shows that we have to select the SoC FPGA device. If you are not selecting the SoC FPGA device, what will happen is the compiler doesn't know. That means that you select a wrong device. Then the moment you enter into the platform designer and then search for the hard processor system, you cannot find out because that FPGA may not have a hard processor system. So it is very important for us to understand that do we have the corresponding SoC FPGA device or have we selected it correctly? And then the one which is circled here will be done in the platform designer. What we are going to do is we are going to create or open a platform designer system. We are going to add or configure the hard processor system IP. And then we are going to add or configure other IPs in the system. Then we are going to connect components and then we are going to generate the system. All these steps we are going to do in the platform designer. And once we generate the system, we take it to the Quartus Prime design software. We instantiate that in the platform designer system in project. We are going to perform analysis and elaboration. We generate the IO assignments and then we compile the project. So in the lab demo 1, I'm going to stop the design with the compilation of the project. In the lab demo 2 of the SoC FPGA, I'm going to introduce you about the debugging technique that is involved. The debugging technique, as I mentioned earlier, we have to see the signal tap logic analyzer as well as the system console, which are ideal for embedded systems. How do we debug that? What is the content that is given in the memory, whether we are able to get the correct data or not? So how do we explore it? When you say we are going to use the system console debugging tool and verify it. So there are 2 parts of this lab. In the first lab demo, I am going to show you till compilation because this does not require the board. But the next one requires the board because it is a debugging exam. So let us start with the golden hardware reference design. What is that? Where do we get the details? I will walk you through that first. There are 2 websites which we need to get into the details here. One is called as the Terasic website. When we enter into the Terasic website, you can see about Terasic, right? And then you can see there is a product. Here you select the SoC platform. And after selecting the SoC platform, you can enter into Cyclone 5 because we are going to create an embedded system design using Cyclone 5 device because we use the light edition of the Quartus software. So let us see, there are multiple examples here. I will explain these mini projects in detail in the afternoon. But let us start with understanding of the D1 SoC board. This is what we wanted to use. When we click the D1 SoC board from here, on the left hand side, you can see overview, specifications, layout, resources, demo, kit contents, and then it shows order now. Now in the resources tab, when you click, it takes you to the page where we have the effective documentation. That means it has the exhaustive documentation of the D1 SoC user manual. You can see D1 SoC user manual. You can choose any revision because since you don't have the board with you right now, and in this particular lab demo as well as in the hands-on, we don't require the board implementation. We can do till compilation, right? Because that itself will take a lot of time for us. We integrate the system and then we can perform compilation. And we can also see that what resources are present on the FPGA side and what resources are present on the HPA side. And then we can also see the FSM, the finite state machine model. What I suggest is D1 SoC user manual, revision F or revision G board, right? This one you can download, user manual. And also what you can download is the D1 SoC CD-ROM, which is revision F or revision G, which is the top one, the first one. The moment you click download, it won't automatically download. It will ask you to become a member of Terasic. This will take only a few minutes for you. Just you click join now, and then you provide your details, and then you can become a member. And once you have the login, just click inside and then come back to the same page and click D1 SOC CD-ROM. Once you download this, what is available there is the question, right? You have the set of examples which are required for FPGA only. You will have examples related to FPGA as well as HPS, and then you will have examples related to only HPS, only the hard processor system. So we can download this D1 SOC CD-ROM. The moment you click it, it will ask you to provide the credentials. Once you provide that detail, you can download the entire CD-ROM. What is present in the CD-ROM, I will show in a while, but I will share this link with you. I request you to go through that in detail. Right. So now, what is another important thing which we need to go through is right. So now, once you download this, you will have the entire information. Okay, this is one. What is the other website which you can go through? It's called as the Rocket Board. So the moment you enter into the rocketboards.org, okay, so here I will take you to the corresponding page, then we can try that. Okay, you can go to the documentation to get documentation for all these boards. Just click project here, where you have multiple projects, right? Where you can have multiple projects, or you can also search here, CSRD. Okay, where you can have multiple information related to this. Okay, so in the documentation portion, you can say getting started, and you can see the GSRD files here. Cyclone 5 SOC GSRD, ARIA 10 SOC GSRD, Stratix 10 SOC GSRD, Agilex SOC GSRD. But what we want is the Cyclone 5 SOC Golden System Reference Design. So here you can see the entire reference design is available, which we can do from scratch. All the informations are available, right? Where you can make communication between the FPGA and the HPS. The information are provided here. We can follow the steps. So this is one place which you can get more details about. Okay. I will share that information also. All right. So let us move on to the lab. What is the objective of this lab? Is to go through the reference design document. Okay, what will be present inside the D1 SOC CD-ROM? I will explain that to you first. If you open the D1 SOC lab manual first, okay, so in this, there are two things which we need to go through. One is, this is an SOC FPGA. That means you have FPGA section as well as you have the SOC section. So if you look into the board, on the FPGA side, you have Cyclone 5, which has the FPGA side. You have a 64 MB SDRAM, 4 push buttons, 10 slide switches, 10 user LEDs, 6 7-segment displays. All these things are required, which is ideal for all digital system design applications, which we have seen earlier. Now you have an hard processor system section, where you have an 800 MHz dual core ARM Cortex A9 processor. You have 1 GB DDR3 SDRAM, and then you have a 1 gigabit Ethernet. All those things, accelerometer, sensor, G sensor, all those things are available on the HPS side. Now, if you see this, right, so I can just reduce it to see, right? You can see that right now. But you can see this is the FPGA side, and then this is the HPS side. On the FPGA side, you can see the 7-segment displays, LEDs, switches, push buttons, etc. And on the HPS side, you can see the UART, USB, DDR3 SDRAM, and you have the Ethernet, and also you have micro SD card slot. So these things are available on the HPS side. Now we need to make communication between the HPS to FPGA. That's the base idea. You can also see that there are ADC that are available on the FPGA. Right? To get more details, you can just download this D1 SoC lab manual. It will have multiple details. Okay, not only that. Okay, it is not only meant for just understanding about the D1 SoC. It also has different examples. Like as I mentioned, you have examples only for FPGA. You have examples only for HPS. And you will have examples of utilizing both HPS and FPGA. That means you are going to use the hard processor system as well as the FPGA both. Now I wanted to use only FPGA. There are examples only for FPGA. And you wanted to use only the hard processor system, right? Only the processor. Then there are examples only related to the processor. Right, what is the question? No, you need to code both, right? So we are going to use like kind of C or C++, right, for the ARM, right? And then you can code Verilog or VHDL for the FPGA side. It is like both are put together into the same SoC, right? So we will have an high-level code, and that could be taken, right? Both would be present right now. I will show you in the debugging where we are trying to use a tickle script and then control how that could be possible like that. Okay, you will have the C code as well as you will have the Verilog or VHDL. Both will be present. Right now, let me just explain you about what is present inside the CD. You have the D1 SoC system CD, where you will have 5 folders. The moment you download, you can see there are 5 folders available there. The first one is the data sheet, and one is the demonstrations folder, thematic, tools, and user manual. Now, in the demonstrations folder, when you open it, you can see there are 3 folders. As I mentioned, you can see FPGA only, then SoC, then SoC FPGA. When you say FPGA only, that means these examples are related to only FPGA. Okay, you can just download them and use only the FPGA section of the Cyclone file, SoC FPGA. Otherwise, you can have only SoC, right? You can see that as the question was asked, right? You can see the C code here. This is only the HPS section. You can see the specific C code that is written to access only the HPS section. Okay. And you can also see I want to use both. Then what we wanted is the SoC FPGA. And when you open the SoC FPGA folder, you will have the example called as my first HPS FPGA. Just copy that. And we have to create a new folder. And say my first SoC design, something like that you create. Now inside that, you paste that my first HPS FPGA. Inside the my first SoC design, you just paste my first HPS FPGA. After you download system CD, the system CD will have 5 specific folders. But what we wanted to look into is go to demonstration. Inside that, go to SoC FPGA and take my first HPS FPGA. Copy this and then put it into a separate directory. Right now, let me walk you through the lab man step by step right now. What we are going to do in this lab. So this lab is the using Intel SoC FPGAs, and how are we going to perform communication between the HPS and the FPGA? Let us see that. So the first few steps I have explained to you theoretically, but you can definitely go through that in the lab man. So you can see this lab introduces a system on a chip workflow for implementing FPGA designs alongside the hard processor system. So what we are going to do in this is like we are going to do everything in the platform designer, generate the HDL, and take that design to the Quartus Prime design software, and then we are going to compile the design, and then we need to take it to the debugging mechanism later. Right? We can implement the design onto the board, right? And then we can perform debugging. That is the kind of logic which we can try right now. Just give me a minute. Sorry. Okay. So the objective of this lab is to introduce a system on a chip workflow for implementing FPGA designs using the hard processor system. So what we are going to do is we develop the design in the platform designer system, and then we are going to perform the parameterization. That means we are going to bring all the IPs. That means it is already there. We need to check, okay, whether the parameters are there. And we wanted to include something, yes, we can include, and you wanted to remove something, yes, you can, or you can modify the points. And then once we do that, we can implement that onto the DE1 SoC Intel FPGA development kit. So the board revision as well as the system CD links are provided already in the lab manual. So this is the one which I opened and showed you in the Terasic website. If you are not able to recollect directly, you can click this link from the lab manual, which will take you to the board revision and system CD. So you don't need to worry about the board, because if you don't have the board, there is nothing to do with the board revision here. What I suggest you is like you take the latest board revision, what is available there. And if you have the board, then if you look at the backside of the board here, you can see there are 2 digits F0. That means it is F revision. It is a revision F development kit. Right. What I suggest is you directly download what I showed you. Right. That is available in this place. You can see that. The first one, D1 SoC system CD.zip. That is the latest one that you download. Okay, now let us start doing the lab. After you download the CD-ROM, directly create a new directory, copy that my first HPS FPGA into a folder, and we can open the project. I will close the remaining things. Let us start with a open project. Go to C drive. My first SoC project, SoC design. And you can see my first HPS FPGA. Inside this, you will have the SoC system.upf. Click that Quartus project file and save open. Right, whenever we open this, you can see that down it shows that the SoC system was previously opened in the Quartus 2 software version 13.1, and it can be upgraded, or it need to be ensure that this IP need to be upgraded to the 18.1 version, which we are working right now. So whenever you see the yellow banner, please ensure that you launch the IP upgrade. The moment you launch the IP upgrade tool, it is asking you that we have to see the regeneration status, right? It is not success. So you click here, perform automatic upgrade. So you can see that the moment we say perform automatic upgrade, you can see that it is regenerating the IPs for our corresponding version. You can see that. Let us wait for a minute. Let it complete. Meanwhile, what we can also go through is in the presentation, I showed you the flow, and you can see this slide because this will give you a good idea. So always whenever we create an SOC project, we have to choose an SOC device as the target I mentioned. How do you know that we are choosing the correct SOC device or not? That's what this slide may help you out. First thing is you have to see the Cyclone 5 SC, SX, ST. That means the S stands for SOC. ARIA 5, SX and ST, ARIA 10, SX, and Intel Stratix 10 SX families. So all these are SOC FPGAs. Along with that, you will also have the Intel Stratix 10 MX FPGAs. They're also an SOC. So you can see down, as I mentioned, while creating the project, you can see it will show HPS CPU cores, where you can see that in this column, it will show you whether that is an SOC FPGA or not. Because in the HPS CPU cores, it shows 0. That means then you are choosing a wrong device. All right, so this is known to you earlier. So let us wait till the part completes the process, and then I will walk you through that. Now it shows 61%. Let it complete 100%. Right now, you can see on the right-hand side, you can see success. Regeneration status, it shows success. Okay, and you can also see that it has upgraded. So the IP upgrade requires the IP cores, the QIP or the QSys file, which is our platform designer file, and that need to be upgraded to the corresponding version because we are using the 18.1 version here. You can say close here, and let us directly move on to the platform design. Click here tools and go to platform design. Okay, now when we say SOC system.qsys, okay, this is our qsys file. Just click that file and say open. Now you can see this is the platform designer window. Now you have the HPS, which is the ARIA 5 or Cyclone 5 hard processor system. You have the parallel input output, PIO LED. You have on-chip memory. You have the interrupt. You have the JTAG UART. All these devices that are connected. Now, what is the easiest way to understand is how the FPGA side. Now you can see that the on-chip memory, which is the Avalon memory mapped slave, is connected to the AXI master. That information we can see that how that connection happened. That information we can get into. Now let us double click this HPS, which is the hard processor system, and get into the details. As I mentioned in the earlier example, you can see the AXI bridges, which is FPGA to HPS interface with 64-bit. And then you can see lightweight HPS to FPGA interface with 32-bit that is provided here. And now what we can just modify, we wanted to just change some of the configurations here, we can definitely modify. So what I'm just trying to do is, there is an enable FPGA to HPS interrupt is there. If you want, we can just, it is checked there. We wanted to uncheck it. Let us try that. Right. So just say uncheck. The moment you change any of them, which is given in the golden system reference design, you can see there is an error. It shows that, okay, there is a missing connection start. And it shows that remove dangling connection. There is an error. What we should do is, if there is any problem with respect to dangling connections, we have to rectify this error before you generate the system. What we should do is go to system and then you say remove dangling connections. So what we need to understand is that the platform designer itself will give you some hint whenever we try to change the system based on our set of applications which we are targeting for. Now what we are trying to do here is, we have seen the FPGA interfaces, axis bridges. Then you can see the peripheral pins. In the peripheral pins, you can see what is very important here is which devices are unused or set. That information we can see here. So let us go through one by one here. Ethernet media access controller, it shows it is unused. And the NAND flash controller, it is unused. Whereas you can see here quad SPI flash controller, USB controller, and the SPI controller, you can see they are showing unused. But then you can see that UART controller, that is set. So which peripherals are set and which peripherals are unused, that information can be seen in the peripheral pins tab. As I explained earlier in the demo, you can see HPS clocks, and also you have the SDRAM where you can configure it for DDR3 or DDR2 or LPDDR2, whatever informations are required. That information can also be provided. Now you can come back to the system contents, and if you want to add any other custom IP, that you can add. Okay, I will show that in the afternoon hands-on lab, how we can bring that and then complete the system also. Right now, what we can do is, like, we can generate the HDL. That means we have just modified one specific interface here. We just changed the component. After changing that, okay, it is shown an error. Now we rectified that error by removing the dangling connection. Let us generate the HDL. Once you click generate HDL, okay, now we will get synthesized files for compiling the system, and simulation files also will be available. Just click generate here. So once it completed successfully, close it. So we can instantiate the SOC system, and let us see, are there any errors there? If there are no errors, and if it is just running with warnings, we can just complete the process, and then we integrate this design in the Quartus Prime design software. Now you can understand that the earlier case, we were just doing only Quartus Prime design software. It was taking less than a minute. Now we are trying to do an embedded system design, because you have a processor, you have memory, you have peripherals that are interconnected in the system, and then that need to be taken into the Quartus Prime design software. You can see that it runs for 2 minutes, 3 minutes, sometimes 5 minutes also. Right? If you are compiling the design, it will take more than 10 minutes also sometimes. Let us close this. And what is the flow we have seen so far is, like, we have in the typical design flow, we opened the SOC FPGA device project, and then we have gone through the platform designer. We have connected the components, you generated the system. Now what we need to do is, we have to instantiate the platform designer system in project, run analysis and elaboration. Then you wanted to do any pin assignments for DDR or any specific scenario, that could be done. We can compile the project. Then I will take it to the debugging mechanism later. Okay, let us perform analysis and elaboration. All right. So since it has completed the analysis and elaboration, we can go to netlist viewers, go to the RTL viewer here. Now we can expand it and see. Now this is our FPGA. Now you can see the HPS side here, which is the SoC system. And you can see HPS, which is the hard processor system. And you can see how that is getting connected with the UART, with the clock, with the memory. All these information can be seen. These are 50 megahertz clock, which is available in the SoC. All right. Now what we can continue is like we can continue performing compilation of the design, because definitely it will take time. It has to perform synthesis, it has to perform filter operation, and then we are going to compile the design. And once we compile the design in the resource utilization, we can see that what resources are taken by the FPGA side and what resources are used on the HPS side. Both we can see that in the hardware design. And we can extend this design, and then we can see that how debugging can be performed by connecting the board, and then we can debug that with respect to signal tap and the system console. Right, let us first perform compilation of this design. Right, so while it is performing the compilation, there are a few important slides which we need to look into. Let us go through that one by one. So we have seen till here the first section, which is called as the general section, that has the different set of interfaces that are acquired, where we have the control signals that are exposed to FPGA design from the HPS. So from the hard processor system, there are some control signals that need to be taken care. We have standby and event signals. We have the general purpose signals, which are input and output to the HPS. And then we also have various debug interfaces, which I showed you right now with the kind of logic, right? So let us try that kind of options also. Now, what is very important to note down from the block diagram is you can see in the block diagram, when you directly click HPS, you can see there are interfaces like F to H. That means it is FPGA to HPS, and also you can see HPS to FPGA, and then you can see GP, stands for they are the general purpose signal. If you wanted to enable the general purpose signals, we can enable that, and you can see FPGA to HPS slave interface, and you can see HPS to FPGA axis master interface that are available. The master bridge and the slave bridge interfaces are also available here, and you can get the signals here. When you click here, show signals, then you can see that signals also down. So here it is inactive. That means you didn't select that. Now, the moment you select that show signals, you can see the signal down. What are the signals that are available related to that signals? We can see it here. This is on the left hand side, and this is given on the right hand side. So this is the detailed picture of showing what are the different set of interfaces, bridges that are available. You can see here bridges available FPGA to HPS, the first one. Then HPS to FPGA, where you have HPS to FPGA axis for master interface. Then lightweight HPS to FPGA. These are the connections. You can see here 32-bit axis advanced extensible interface. And then you can also see the SDRAM interconnect. So we can refer it to the Cyclone 5 device SOC handbook to get more details of the HPS and FPGA bridges and understand how they are getting connected. But this in the golden system reference design, you don't need to change anything there. But even if you wanted to modify any of the settings, then by going through the warning or error, we can easily rectify, because it tells you that how do you remove the dangling connections, or how do you connect the processor, that means with the clock reset and all the mechanisms, that you can definitely understand that. And you can also see from the SOC lab manual that what kind of errors are predicted, and for those errors, what are the different set of solutions, right? That will also be given to you. So this is like where we can see that what is the kind of boot source, like you can see what is the kind of booting, right? You can say boot room, that is the different logic that could be generated. In the HPS and the clock reset tab, this is very important for us. You can see what are the input clocks that is available on the FPGA side, and then what are the clocks that are present on the HPS side. So this will provide you a good idea on what is the main HPS clock and the clock inputs that are coming from the FPGA into the HPS. So that information also can be seen. So I showed that also during the demo. And this one will show you what are the peripherals that are enabled. And for example, which peripherals are connected and how they are not connected, those informations are also shown in this slide. So once we do that, we can instantiate the hard processor system in the platform design. You can see that in the HPS, you can see how the connection happens. On the left, you can see the moment hard processor system you select. It shows that some of the components are inactive. That means it shows that ARIA10 hard processor system inactive and Static 10 hard processor system inactive. But then you can see that ARIA5 or Cyclone 5 hard processor system is active because we have selected the Cyclone 5 device. So after completing the design in the platform designer, we should take it back to the Quartus Prime design software. As I mentioned in the discussion, right, there are two ways to perform connection. One is directly you can click the open dot to make a connection, or you can right click the interface and then whichever you feel comfortable, that would be possible. Right? It is very easy to do that. Right. So this provides you the complete system. How do we generate that with the platform design? So you have the HPS side and also you have the FPGA side. So here you can see H to F, and here you can say FPGA to HPS. FPGA to HPS SDRAM, FPGA to HPS axis slave, HPS to FPGA axis master, and you can also see HPS to FPGA lightweight axis master. So once you have the complete platform designer system, after generating the simulation and synthesize files from the platform designer, you have to take it back to the Quartus Prime design software. That's what is the one which we have done so far. So after explaining that, I will go to the debugging techniques. Right, let it run. So we'll wait for a minute. Meanwhile, what you can also see is like how many memory bits it has taken, and how many registers it has taken, and how many pins it has taken. All these information are there. After we complete this, this ends our second session, and then we will move on to the third session immediately. So in the third session, we can connect the board, and we can understand the objective of debugging mechanisms. Here, in the yesterday's discussion, we discussed about the debugging mechanism with respect to the signal tap logic analyzer. I will just show you some glimpse about it today. because we discussed in detail in yesterday's afternoon session, but one or two slides I will show you today. And our focus would be on the system console. So in this particular example, we are going to do both. We are going to connect the board and perform both tasks. Right. So before it completes, let us just walk in through the third section, and one or two slides I will complete. Okay. Now in the earlier section, we did till compilation. What is the guarantee that, okay, what is available right on the board, I wanted to see whether it is working correctly or not. So that means we wanted to see that the Quartus Prime debugging tools are available for all NIAs as well as the SOC systems. Right, now let us perform the kind of debugging techniques. One is on the system console and the other one is on the signal tap logic analyzer, which we discussed yesterday. So let us complete the signal tap portion, revising 2-3 slides. I can show that to you. And then we will go back to the previous lab demo. After compilation, what happens, we will see. And we understand the system console, and then I will show you the demo of debugging SOCs using both system console and a signal tap logic analyzer. Right. Now, what is system console? That's what we need to understand. It helps you to perform register or address level transactions through a scriptable, that is a tickle environment, without the software. And you have signal tap 2 logic analyzer, where we can do signal and logic level FPGA hardware debug. To give a quick glimpse about the signal tap, what we discussed yesterday, I can show that to you. What is the objective of this session is to understand and select appropriate debugging tools for FPGA designs, where you have the signal tap logic analyzer as well as the system console instrumentation. Right, so let us go through some slides of the signal tap embedded logic analyzer, and then we will go back to the same demo. So a quick recap in the yesterday's session, you can see that what is the advantage of signal tap? No external equipment required. Don't need to figure out stimulus since it is based on the actual hardware. But the problem with signal tap is it uses lots of memory resources inside the chip, and it can change the timing of a design, and it requires recompile, which takes time, definitely. Okay. Now, give a quick recap about signal tap. You can see that you don't want an external logic analyzer. The signal tap is a logic analyzer made up of available resources inside the FPGA. That's what we have discussed in detail yesterday. Now, what is very important is that we are going to capture the data through the standard data connection typically used for programming the device. That means we are going to program the SOC right now. After programming the SOC FPGA, we are going to see, right, in the signal tap and the system console, what is the output. So that will give us a good idea whether we are debugging that in the right direction or not. So what are the pros and cons of the signal tap, which we have seen yesterday, but then just give a quick recap of that. Advantages, you can tap the signals which are buried deep in the design, and we don't require any reconfiguring, recompiling, reprogramming, nothing. But the greatest drawback, like the cons, if you see, definitely it will take some set of logic elements and memory resources. The signal tap logic analyzer will take LEs and then the memory resources. And because of that, it won't change the base functionality, but then there is a change in the timing. And we also need to have a active JTAG connection. That is important here. All right, now let us go back and see whether it has completed. Now it shows 100%. And you can see what are the resources that are taken by the FPGA side and what are the resources that are taken on the HPS side. We can see, go to the fitter, expand the resource section, go to resource usage summary. And here we can see that how many adaptive logic modules it has taken ALM. And you can see that total logic array blocks, LABs. And you can see the dedicated logic registers that are useful. And these are the informations that are present on the FPGA section, where you can see the number of pins, memory, etc. But here you can see hard processor system peripheral utilization. Here, what are the informations that are okay? So how the signal tab can change the timing? If you say the signal tab will take some resources along with your design. Your design uses some set of logic elements and then it uses some memory. Signal tab will take some more logic elements and some more memory because it is an inbuilt logic analyzer, right? It is an embedded logic analyzer. It is going to take some logic elements and memory. So if there is some logic element and memory, there is a register to register path, right? You have a reg to reg path, you have an input to reg path, there is a register out path in the timing analysis, right? The number of timing paths will get increased. Earlier, you will have less number of timing paths. Now you will have more number of timing paths. Even though it is not affecting the functionality, the number of timing paths are getting increased. Because of that, there is a change in the critical path. Earlier, something may be the critical path. Now, something may be the critical path, right? So that is what we should be very careful, right? Earlier, the area was less. The memory consumed was also less. Now, because of the signal tab, it is going to add some more hardware, right? It is going to take some more resources from the FPGA. Because of that, there is a change in the number of timing paths. Since the critical paths are getting affected, it will affect timing. Yeah, thank you. Let me explain this. So you can see the hard processor system peripheral utilization. And you can see that here you can see, right? This is your HPS side. And you can see this is our FPGA side, M10K block. 68 that is used out of 397 that you can see. And all these informations are captured here. Now, what is important for us? We can see two important things here. One is after you perform compilation, see the technology map viewer. You can see this. And now this is your HPS component. Similarly, you can also see the FSM viewer. So this is the finite state machine which is available inside the design. You can see how big is the FSM, you can see that. Right? And you can also see here the source state and the destination state and what condition it will transit from one state to another. You can see that. Okay. Now, what is another important thing which we can explore is the chip planner. Go to tools and then you can go to the chip planner. Okay. Now, this is your FPGA section. And this is your HPS section. I explained in the presentation that in the Cyclone 5 device, this is your hard processor system. And this place is fixed. And this is your FPGA section. And here you can see the resources that are used by the design. These are your memory resources. Okay. Right. So this ends that lab because we are just going to explore this step and ensure that design is examining all the parameters properly. And we can also save the system completely and then come back and see what are the resources that are taken on the HPS side as well as the FPGA side. That's what is explained. And you can see the conclusion here. Right, we downloaded the Golden Hardware Reference Design Project. We examined the platform designer system. We examined the parameters and checked what peripherals are enabled. And we understood the Axibus interface connections, generated the HDL code, compiled the design in Quartus, and analyzed the utilization reports. Right, so let us understand the debugging process right now. Before entering into that, let us solve what is the system console and then we'll continue. Okay. So these are the steps related to the signal tab, which I will just take it to the next step, which is called as a system console. The signal tab has been shown for the FPGA device yesterday, but now I wanted to show both the signal tab and the system console for an SoC debugging today. That's what I clubbed both. Okay, what is system console? Let us understand that. The system console is a debugging tool which extracts away the complexity of viewing digital waveforms. And it is a super handy tool for reading and writing memory mapped elements. We can see that we can insert and compile once. Everything in memory map is settable or viewable. After the implementation, we can just check whether it is fine. And able to build GUIs to interface with FPGA. The only problem with the system console is the odd syntax because it looks completely a kind of tickle interface where we have to be very careful in managing the syntax, right? Because along with our Verilog VHDL system Verilog with C, you need to go through the tickle syntax also. How do we use this? When you say we are going to again use the platform designer tool, and then we connect the components. After connecting the components, we are going to debug. Okay, so you have the system components ready. You have the IP catalog, you have hierarchy, we have parameters, everything is set right now. After the design is ready, we wanted to verify. Let us take a simple, typical embedded system. We have NIAS, we have on-chip memory, we have JTAG UART, we have the switches, we have buttons, etc. And all are connected to the Avalon interface. You have LEDs, 7-segment display, etc. Now what we need to do is we are adding another master to aid in debugging of system components by accessing memory locations of these components. We are going to add one more important interface and then we cross verify. What is that when you say? That is called as the JTAG to Avalon memory master build. So the system console allows you to see what is in any memory location in a platform designer system at any point of time. It is very important for us. What has been written and what has been read, that information we want. How do you run the system console? When you say to run the system console, we need to add this block in the platform designer. That's all. Once we add this block to the platform designer, we can run the system console and check whether what data we have written and what data which is read, is it correct or not, that we can easily debug. I have an example for it, and then I have the example demo. I will show that to you. Right. So along with the features of the platform designer, you can easily enable the reuse, and then we can reduce the time to market and eases verification. That we knew already. But this the same thing works with system console also. So to have a quick recap, the system console is a quick system level debugging tool for platform designer system. And it has an interactive tickle console. And we are going to debug the design over the JTAG. And in our case, we are going to just connect the JTAG and check the output. So now you can see there is a processor, there is an Avalon master bridge, slave, and that we are trying to connect. All the interfaces are connected to the system console, and we can see what data has been read and what data has been written. And there are two ways to launch system console. One is you can directly through that in the platform designer. Other one is you can use to command shell. I will show you how that could be possible with a simple example. Right, let me walk you through that. So in our Day-5 folder, we have a signal tab demo.qar, which is the Quartus archive file. I will just copy that. I will share the same with you. Go to the C drive. You can say debug and say system console and say signal tab. Both are in the same design like that. Paste that signal tab demo.qar file and let us open the Quartus Prime Design software by closing all these things. Close this project and we'll open that. Debug, system level console, and say open that. Okay, there are two things that need to be explained to you before we connect the board. One, we need to see in the code, we have a 32-bit scratchpad register, and we are going to write some data into the scratchpad register, and we are going to read the output. That's what we are going to do. During the reset, the scratchpad register is having a 0 value, and then we are going to write some value to it, and the value what we have written, that we wanted to see that in the signal tab as well as in the system console. After the data has been written in the system console, we wanted to check that in the signal tab logic analyzer, whether it is able to get the correct data. That's what we wanted to explore. So you can see that during the reset, it is 0. And then we are writing the data. And then during the read interface, we wanted to read that data. That's what is given in the Verilog code. Let us explore the restored files and explain you about the tickle script, which is important before we continue. Go to the C drive, go to the debug system console ST, go to the restored file. And here you will be having a tickle file. To open that, in the tickle file, you can see there is a package. Now you can see set register 0. Now you can see there is a procedure where we wanted to do during the reset operation. It is 0. And we wanted to read the data, and then we wanted to write what when you say ABCD 1, 2, 3, 4. You can see that. We are writing the data, writing the scratchpad register ABCD 1, 2, 3, 4. And after writing ABCD 1, 2, 3, 4 into the scratchpad register, we wanted to read it again in the SOC FPGA. How it works out, let us see. We want to read the data first, is 0. Then we wanted to write the data next. What data we are writing is ABCD 1, 2, 3, 4. After writing the data, again we should read it. That's what is written in the tickle procedure. So we have a start service master. We read the register 0. Then we write the register 0. Then again we read the register 0, and then we say stop. This is what is written in the tickle console. Now we need to run this tickle script in the system console. And after executing this script, we have to again check the output in the signal tab logic analyzer. Okay, now let us perform compilation. And meanwhile, when it is performing compilation, I will connect the board to my laptop. We will program the design, and then we will see the output in system console as well as in the signal tab logic analyzer. Right, it will take 2 minutes. Let it compile. Meanwhile, I'll connect the board panel. So this debugging is for the SOC FPGA board. It's based on the Cyclone 5 device. So we need to connect the power supply as well as we need to connect the JTAG. So just give me a minute. I have connected the board. Let it complete 100%, then we can see one by one. So you can see here it is based on the Cyclone 5 device. You can see the number of ALMs here, how many number of logic elements like adaptive logic modules it has taken, like that you can see. And also the registers, pins, memory blocks, everything. It is not very small, right? Because in the earlier case, it was taking less resources because it is only in a specific RTL design. But now you use an SOC. Okay, now I have connected the board. I need to perform two important operations right now. One, I have to program the device. Only then we can debug the SOC. In the earlier lab, we don't require it because we compiled and then stopped. And there was a last step that you need to debug the design. You need to take it to the hardware. That's what we are continuing in this lab. Along with that, I wanted to show you both the debugging mechanisms, the signal tap, as well as the system console. So in this specific lab demo, we can get the idea of both signal tap as well as the system console. Now we click tools and then we can go to programmer. Again, simple recollect. You can see that run simulation we have done, timing analyzer, planner, netlist viewers, signal tap, right? And then we have also seen IP catalog, platform designer. We will do this NIAS too, right? Later. First, let us start with the programmer. So now the moment you see that signal tap demo, you have only the FPGA device, right? Because when it is an associate FPGA, you require the HPS as well as the FPGA. In the Max 10 device, you will have only one because it is only an FPGA device. But here you have the SOC. That means it is having HPS as well as the FPGA. So we have to say auto detect. And then it is asking that which device. Okay, so you can select because we are sure about the Cyclone 5 device, right? You can see the moment you select that device, it shows yes. You can overwrite. You can see that SOC. That means it is Cyclone 5 HPS. Okay, you can see CV, which is Cyclone 5 HPS. Now what we should do is, the moment you select that, you need to say program configure. Before that, what we should do is, we should add the file. Click here, edit, and say change file. Inside the output files folder, you have a signal demo.sof file, just save open. Okay, now you can see that it shows in the output files. Signal tap demo.sram object file is there. We have to click here, program configure. After we say program configure, we should say start so that it should show 100% successful. Then we can see the output in the signal tap logic analyzer after implementing the design onto the board. Then we can also invoke system console and check whether it is working fine. Okay, now let us start with this. Now first we'll say click start. And once it shows 100% successful on the right hand side, we can minimize this window. Come back to the quarters. Here you have to go to tools, signal tap logic analyzer. In the signal tap logic analyzer, you can see that what is the data we wanted to check right now. So this is what we explained you. That the signal tap will take number of logic elements. It will take some memory bits. Right. Now, what is very important for us is we should run the analysis and see during the reset what is the value. And after completing the script in the system console, what is the impact? Let us try that one by one. Now let us go to processing and say run analysis. Once you run the analysis, we wanted to see what is the output. So say stop analysis. Now you can see that during reset, the values are 0. You can see here master, address, write data, everything you can see it is 0. Now what we wanted is we wanted to write the data into that in the scratchpad register, and what data we have written that we wanted to read, right, in the signal tab. That's what we need to do. What we can do, we can minimize the signal tab also. Come to the quarters main window, go to tools and say system debugging tools. You can see that system debugging tools, and you can see system console. Open that. Okay, so now once you open the system console here, say here PWD, that means it is in this directory now. You can see that it shows debug system console ST signal tab demo restored. Now, how do you run the tickle script is the command called source. Okay, so what we should do is source reg underscore access dot tcl. We are going to run the source file. Just say enter. When we do this, you can see that earlier the scratchpad register is showing 0. And we are writing the data as 0xabcd1234 into the scratchpad register. Writing the data into the scratchpad register, it shows. After writing the data into the scratchpad register, again we wanted to get output. That means we wanted to come back again to the signal tap logic analyzer and see whether it is able to read this data. So we minimize this system console and come back to the signal tap logic analyzer. Okay, so that we will try now. Now in the signal tap logic analyzer, again we should go to processing and say run analysis. Now it is acquiring the data. Now go to processing and say stop analysis. Now once you stop the analysis, you can see that ABCD1234H, ABCD1234H. So when you expand this, we can see that this is the data master, which is the write data. And you can see that the data master read data, that is also ABCD123. Now this is the way how you can debug the SOC FPGAs also. Now we have understood how to develop the design, and we have also seen that how we can debug them. That is very, very important for us, right? Because with the debug mechanism, we can see that what is the data that is available, what data is written, and what data has been captured. All these informations would be known. So without knowing that, it is very tough for us to compare. Right. So it is not only just implementation onto the board, right? Because how do you know that in the SOC that what data has been captured and what data is coming into that like that, right? In the small design, like we have seen that in terms of memory yesterday. In that itself, if you see here, it's a dual port memory. In the model sim simulation, we should look into 2 ports, and luckily all the clocks, 2 clocks are working at the same frequency. Sometimes they are different. Then you have to enable them, and you should verify them appropriately in model sim simulation only. And the same need to be captured in the signal tap logic analyzer. It is a challenge, right? But it was a small design, so we should. But if the design becomes complex, then it is very tough for you to do that. Okay, and then debugging the SOC FPGAs are quite challenging. So in order to do that, we have system level debugging tools, which is called as a system console, which helps you to see the data what is written into. So I'll close this, and I will share these details with you. You can definitely do compilation, get the details of it, but you need to have the board to continue the specific lab to get a logic, because the labs LAN setup does not support the signal tap and debugging options at this junction. Right? Are there any questions? Okay, so I don't think so. Any other questions are there? Stop sharing and see anything on the Q&A. Okay, so I will just again share the same link and explain that to you. Then we will go to the last step. If you go to the basic website, right, you go to the DE boards or SOC platform, okay, and you select DE1 SOC board, and on the left hand side you can see resources. Select that and select the first one, DE1 SOC CD-ROM revision F revision G board. The first one. On the right hand side you can click down. This is what we require it for today's lab. Okay, once you download that, you can have a folder where you can see there are few folders inside it. What we wanted for today's hands-on lab is go to demonstrations, go to SOC FPGA, and we are going to take only my first XPS FPGA. Only this lab, that's what we did. But there are other examples which you can practice. Here itself, there are 4 reference designs. And in SOC, you have 4 reference designs. And in FPGA, we have around 10 references. So you can see 10 projects plus 4, plus you can see 4. Around 18 projects we can do that with the SOC FPGA. All right, so let us go to the last step. It's called as the embedded system design using the NIAS processor. Only the hardware design flow has been explained to you. Today we will complete that with the software design. All right, so let me walk you through some of the steps, then we can continue with that. This is the last step which we have seen, the system console GUI, where I explained you about how do we check the output and how do you run the script. There are multiple reference documentations for Cyclone 5 SOC FPGAs. I can share this with you. You can click the link, it will automatically take you to the corresponding page. You can download and get the details of it. Right, so let us spend some time with NIAS 2 and complete the software IDE environment. What is the objective is we are going to do an embedded system design with NIAS. In the earlier lab, we did embedded system design with NIAS, only till hardware design. We didn't do the software. Today, we will try to do the software design. Right now, I can show you a quick demo of how do we do that with the Eclipse. So we have a platform designer system development tools. There is no change. How did we do for the SOC FPGA? Exactly the similar way. We can do this for the NIAS 2 processor system also. So the advantage of NIAS 2 is like we have an integrated development environment, which is an Eclipse. So that will be helpful for you to do a bare metal application without the operating system. What is NIAS? You have multiple informations right now, but then still some of the information, since we are comparing that with the hardcore processors, I need to show you. It is a configurable 32-bit embedded RISC processor. It is compatible with all the Intel FPGA devices. And then it is the lowest cost. You have a soft IP core, royalty-free license. And performance is greater than 400 dBps. This F stands for the fast, and you can see that is for the ARIA 10 devices. What is the size taken from by the NIAS in the FPGA design when you say? When you are targeting it for economy, it will take around 800 logic elements. And if it is fast, it can take up to 1600 logic elements. Right. So what do we require? We need to complete the hardware design and we take it to the software. So for that, we need to use the Eclipse, which is called as software build tools, which is called as SBT. Okay, so how do we work out when you say you require an SOPC information? We require a system on a programmable chip information that would be given from the Quartus Prime design software. That means with the platform designer, that will go to the Eclipse. Then we will complete the system. All right. Now you can see that it is optimized for speed as well as for size. That is for area. Right. So you have the hardware. That is a general flow like platform designer, but then we are also going to do the software. We bring both and we verify that in the intellect. Right. How the flow will look like, a small specific logic I'll show you right now. Take the platform designer and you generate the HDL, take it to the Intel Cortex Prime design software, generate the SRAM object file, and in the software side, take the SOPC information from the platform designer, take it to the NIAS to software build tools. That can take either C or C++, anything. Then you generate the ELF file, and you require both SOF file as well as the ELF file, both hardware and software, both need to be taken to the board. That is the flow which we need to follow. So this is called as the NIAS to SBT flow, which is called as the software build tools flow. Okay, how do we continue that? I will show that demo now. So this is the NIAS lab, which has been shared with you earlier, but this is being done with hardware design. And I have stopped with hardware design. Today we continue with the software design. Right, so let us open the folder and you can see embedded. It's a short lab as well as a long lab. As I suggested, you can go ahead with both, but we can just continue with the shortened edition of it right now. Copy the design files, take it to the C drive, and say NIAS design. Okay, and then inside that you. All right, now we can again go back to the Quartus Prime design software. We closed all the projects. Go to open project, C drive, NIAS design. Inside the design files, you have the semi-completed.quartus archive file. You open that. Okay, right. So now we should go to tools, go to the platform designer. Okay, now click QSys file, open it. Now listen, right? If you go through here, we have the clock and then the CPU, on-chip memory, button, LED, switches, and then we have 6 hexadecimal displays, X0, X1, X2, X3, X4, X5, all are connected right now. From the lab manual, what is important for us is like we are going to add one component which is called JTAG UART component. We have to add that component here. The rest of the things are just basic information about the DIT and light board that you can just skip it. Directly add the JTAG UART. So go to the platform designer. In the IP catalog, type JTAG UART. So double click that. Finish. Now you can see there are multiple warnings. So what we should do is connect the clock first. I'm clicking the open dot. You can see that. You can also right click and say you connect the reset. That is also possible. Right? You can collect the JTAG slave and you can also connect the interrupt request if you want. Now you can see there are multiple errors. And how do we rectify these errors? It's like there is a problem with respect to address conflict. Tell the tool system assign base address. All the addresses conflicts are changed right now. Okay. Now what we can do is we can generate the HDL. Click generate. Close. So say close here. Now what we can see is like the HDL is generated. Now we can minimize this. And we need to come back to the Quartus Prime Design software. You can see generate HDL. Once you finish it, you need to build the top level design. You come back to the Quartus Prime Design software, and we need to add the file, right? Which is we added that the instance, right? So that QIP file we have to add. Okay, so now we should go to the Quartus. In the project add or remove file, you see there are 3 dots. Click that. Go to NIA setup V2. Go to synthesis. There would be a QIP file. Just click that file, say open, apply, then we can say okay. This is what is explained in the lab. Let's go through that. Now, once we apply this, we can check in the assignment editor whether all the pin configurations are perfect. Okay, this also I have shown you earlier, but then it is better to check it once again. So go to assignment and say assignment editor. So here you can see. The one clue is like all the LEDs and the switches, right? We knew that what are the values that you can cross verify here. LED locations, switches locations we can see. Okay, right. Now let us minimize this and we can compile the design. Let it get compiled. Meanwhile, we'll connect DIT and light. So let us compile the design, not compile. Okay, just give me a minute. Okay, so what are the steps that are available in the software? Let us quickly see that. We are going to create the software for the Hello World design. So we have a software build tools, SPT, that is available in the DS2. We take the application and then you have a BSP, which is called as the board support package, which have the drivers for translating the printf commands to the appropriate instruction to write in the terminal. You can see that. What is very important is from the platform designer, we would have got an SOPC information file. So this SOPC information file will inform our Eclipse, right, on what your platform designer system contains from the hardware. That means it is the handoff between the hardware and software. You take that from the hardware and give it to the software, which is the Eclipse. Now, once we provide this information, what we are going to do is we are going to debug this, right, and see whether you are able to program the board. And after programming the board, we can check whether the software works fine, because we have the hardware, that is your SYF file, and we also have the ELF file, which is a software executable file. Both the software executable file and the SYF, right? Both we are going to put onto the same. This is what our lab. Okay, so I will just show one. The other one is also there, which you can also try. There is one more lab which you can try that as a practice. So let us go through the steps now. We completed the hardware design. Let us start the software design now. Go to tools and go to NIAS to software build tools for Eclipse. Okay, so IP catalog we have seen earlier, system debugging tools, platform designer. Now click this. Okay. So now you can see that. For example, I wanted to remove that, what is already available, and we can create something. We can delete them. Okay, right. So let us start from scratch. So in the NIAS software build tools, we have to create a new project. We can say new NIAS to application and BSP, the board support package from template. So we have to click that, file, new, and say NIAS to application and BSP from template. Click that, we can open it. And here we have to select the hello world small. That is okay. But now you can see that the SOPC information file name is required, because you can see that you have to specify an SOPC information file, because that comes from the platform designer as an input to the Eclipse. You can see that he has to set up V2 SOPC information. The moment you give that SOPC information file, this is based on a bare metal without the operating system. Where it is available, that information will give. The name of the project we have to put. So as mentioned here, you can give any project name. First you give the SOPC information file here. And after you select it, you can give any name. For example, hello world SW is there. And you have to select a specific template from that, okay? So I'll just say here, hello world. And say new. Okay, and you have to select here hello world small. Right, and this example, right, is going to run without the micro COS or RTOS, because it is just a bare metal application. Let's say finish. Okay, now we need to modify the C code. Like the C code has some information like small.c, but then we already have another C code where we wanted to just copy that and then we can modify it here. Okay, let us open that hello world small.c C code, which is available here. Okay, and that C code we can modify it with the one what we have. Right, so what we can do is we can go to our project where we have the NIAS design files. Here you can see there is a hello world.c file. Just you can copy that from here and you paste it to the information. And you can save it now. Right, so once you save this, we can program the design. Okay, so we can program and then we can say build and then we'll continue. Project, you can say build on. Right, now what is important is we have to program. So what we should do is we should go to the hardware here. Means if you go through the manual, we have to go to the device manager and then you can check whether the USB blaster is showing or not. If it is not installed, then only you should follow this step. If it is already installed, directly we can program it. So what we can do is, like, first we will program the SOF file. We minimize this. Come to the Quartus Prime Design software. First we will program the SOF file. Go to programmer. And you can see there is a top.sof file already there. Just say start and program. Okay. Once this is done, we can go and take the ELF file, and that we need to run now. So now it is time to download the ELF file. What we should do is there would be run NIAS to where we need to provide the connection. That means where we need to check whether that USB blaster, that this connection should indicate that the Eclipse has been connected to the USB blaster. Then only we can run this ELF file. Okay, so what we can do is we can say run as NIAS to hardware here. Okay. Okay, so now we can cross verify. You can see that shows that it is processed and it has performed. So now if you go to the console, you can see that, okay, it is verified and it is using the cable USB blaster, and then it is able to verify. So what we have done is we have taken both the ELF, that means we took the ELF file as well as we have downloaded both. That means you take the SRAM object file as well as we took the ELF file. Both are done. Now the same could be also checked using the 7-segment display, but this is available in the lab manual. I request you to go through this later. You can use all the 7-segment displays, and each and every key has different options that you can try it on your own. So this ends the NIAS 2. Right. Now let me directly take you through the presentation logic here. What is the plan? It's like we have seen introduction to Intel SoC FPGAs, embedded hardware design flow, NIAS 2 software processor and embedded system design using NIAS 2, golden hardware reference designs, embedded system using Cyclone 5 and ARM, debugging techniques, signal tap and system console, implementation on SoC board, and there was a lab demo I showed you, and we are going to do that hands-on lab in the afternoon. Along with that, I will also show you some of the specific reference designs and how do we do mini project using the Intel SoC FPGAs. So I will stop sharing. If there are any questions, I will take it. Otherwise, it is over to them.
Yes, Padmanabham sir.
Yeah. So I have done. So there are no questions here. You can take over.
Thank you, Padmanabham sir. So dear participants, now you can take the lunch break. Before that, I would like to announce one thing. Today we are having second MCQ of this joint faculty development program. It will be taken by 4:30 p.m. The link will be shared with you in the Google Drive, and it will be activated at sharp 4:30 p.m. only. Thank you, everyone.
Thank you so much, everyone. Let us meet by 1:30. Thank you, Biplav. Let me start. Good afternoon, everyone. So I will share the informations in the Google Drive. I will let you know what are the informations you can see there. I will also put the zip file if possible. You can just go through that. Those who have not downloaded, you can take it from there. And you have the SOC lab in detail, which has all the informations related to the Day-1 SOC. I will share this with you. Please go through the steps and complete the SOC design lab. Meanwhile, I'll introduce you about how can we do mini projects with the Intel SOC FPGAs and what are the different options that are possible with the D8 and Nano. I will show all those information with you. Right. So let me share the lab files and then update you right now. I have shared the lab files in the drive, and I will also share slides soon. Meanwhile, you can start downloading that, and I also put that D1 SOC CD-ROM file also in the drive. If you have not downloaded it, you can take it from the drive also. Go to the demonstrations folder, take the FPGA, take the my first HPS SOC example, HPS FPGA example, and then you can go through the lab manual.
Padmanabhan, sir.
Yes.
So we can start with the session.
I have already started the session and I gave the inputs also to them. Now I am sharing the files in the drive.
Okay, sir. Okay, sir.
Yeah. I'll share the files in the drive and then I will again explain them the steps. Just give me a few minutes. Yeah. Yeah. See what exactly need to be right. I'll just again explain to you clearly. In our website, go to the SOC platform. Okay. And open the D1 SOC board. Go to resources and select the D1 SOC CD-ROM. Okay. So here, this one you download. And if you wanted to take that directly in the today's drive, right? I have pasted that also. D1 SOC system DD CDs.zip file is available here. You can download from our drive and extract the zip file. And once you extract that zip file, okay, now let me see here. You open this D1 SOC CD-ROM. Okay. You can see that inside this, you can see demonstrations. And here you can see SOC FPGA, my first HPS FPGA. So in the Google Drive, right, you have this D1 SOC system cd.zip file. So I have pasted that you can take it from the drive. Okay. Once you extract it, you will have 5 folders here. There you can go to demonstrations, go to SOC FPGA, take my first HPS FPGA, right, and then put it in a separate drive, and then you start exploring the lab. This is the lab I have shared. You can also go through the links what is provided. Okay, so if you have not downloaded, I have already tested that in the drive. Please take it. I continue the first lab. This is the use in Intel SoC FPGAs lab. To complete this lab, parallelly what I will do, I will share the PDF slides in the drive, and I will also explain you how to do mini project using the Intel SoC FPGAs and what are the different set of applications where we can target using the Intel SoC FPGAs. I'll show you. Okay, so I'll just stop sharing. Is that clear? Okay, so I will share the PDF slides right now, and please start working on the lab one. Then I will also give you a demo on the mini project using Intel SoC FPGAs, right? Give me a few minutes. I will share the PDF slides with you and you can start working on it. Those who have not downloaded, please download that from our drive. I have kept the D1 SoC CD-ROM. Go to the demonstrations folder and open SoC FPGA and take my first HPS FPGA example. And please go through the lab manual and complete the lab. Okay, so let me start the D10 Nano. Like what is the kind of projects we can do with the SoCs, right? Let us understand about the D10 Nano. Why? What is the need for understanding D10 Nano? Let us explore that in detail right now. So this is an embedded and robotic board that is available, and it has 100K logic elements and 1 gigabit Ethernet, and then you have RFS data card, and that is for IoT wireless connectivity, and it includes Bluetooth and Wi-Fi. And you also have 8 megapixel GPIO camera that is required for the video imaging. So if we get into the details of this, like for example, Intel Developer Zone, and then you go into D10 Nano. Okay, so let me paste this link in the chat. Right now, you can see that it is based on the Cyclone 5 SoC FPGA. Okay, so this kit provides a reconfigurable hardware design platform for makers, educators, and IoT system developers. Why this particular board? When you say this is the kind of board which could be useful for IoT systems, so you can see the industrial use cases where you can use it for IoT systems, industrial automation, and high performance computing. Okay, now what we can also do is like there are multiple informations in the kit, and you can see there are specifications that are provided, and you can see there are compatible accessory boards. And one board is very, very important, which we need to discuss now. It's called as the FPGA Cloud Connectivity Kit. I will share this information in the chat. Please go through that, so that will help you to do multiple projects. Okay. After clicking demonstration, we need to select SoC. You have to select SoC, right? SoC FPGA. See, FPGA is only for FPGA applications. SoC is for only HPS, hard processor system. What we need to select is SoC FPGA. So please go through the lab manual. You have entire detailed information there. Go to SoC FPGA. Inside SoC FPGA, you can see, right, my first HPS FPGA. There will be 4 projects. In that, you select my first HPS FPGA, copy that, put that in the C drive or wherever you wanted, and then you continue the steps that is given in the SoC lab manual. Are you getting my point? Is that clear, or do you have still issues? Do I need to explain that to you? Okay, thank you. So what I say is like you can just go through the lab manual and continue the steps of the first lab. Meanwhile, I have sent you some documents in the chat. Just go through about D10 Nano and what are the reference designs that are available. Right after some time, I will explain you about how you can do multiple mini projects using the SoC FPGAs. Right. I'll be available now. Please let me know if you have any queries in the first lab. As I mentioned, there are two options here. One is called as the FPGA Cloud Connectivity Kit. Okay. So if you type here FPGA Cloud Connectivity Kit, it will automatically take you to the Terasic website. So this FPGA Cloud Connectivity Kit combines the D10 Nano, which is our SoC FPGA. Also, there is an RFS module. Okay. So using this FPGA Cloud Connectivity Kit, it is very easy for us to develop our own FPGA-based application that can collect, analyze, and react to data from the IoT equipment. And not only that, this development kit is certified with the cloud service providers such as Microsoft Azure, and it comes up with open source design examples. So where you can say edge to cloud. And this board also has Bluetooth wireless communication, as well as it has ambient light, temperature, and humidity sensors, accelerometer, and gyroscope. So this is one kind of mini project or the applications which we can do with the SoC FPGAs. So where we can do projects related to edge to cloud. One is the FPGA Cloud Connectivity Kit. Other one is the self-balancing robot. That is also available in the D board's SoC platform only. So if you open the D10 Nano here, okay, D10 Nano kit, okay. The applications of the D10 Nano, right? So here you can see, right? The resources are available here, but you can also see what kind of applications it could choose. Okay, and you can see here, robotic kits. If you click here, this will take you to the self-balancing robot. So this is based on the D10 Nano. So what are the things that can possible is the robot can implement attitude algorithm, perform motion control, and execute movements autonomously. Yeah, you can try that through the specific vendors. So I will share this with you. We can try that with DG key or browser, okay? So these are some of the specific projects which we can work on. And using this SoC FPGA board, right, as I mentioned, there are multiple applications that are available. So I can just show you what are the different reference designs we have. So here you can see what are the different set of projects. You can see that these are the projects which we can see. This could be used as a specific mini project. So to do this, we have an FPGA cloud connectivity kit. You have a digital camera kit. You have wireless connectivity board, servo motor kit, multi-touch LCD module, and LCD touch module. All those things are there. And you can see there are multiple projects that are available. So let me just show you one or two examples here. Let us start with this Flex 4 Smart Globe. So this is a project which uses the Intel SoC FPGA to measure the sensorimeter data. Okay, so I can just show you some case studies. You can see that. So using the Intel SoC FPGA to measure sensorimeter data, here you can see that interactive exercise feedback and detailed pressure and flex display, all those things are used. What is the hardware and what is the software is given here. So in the hardware side, you can see the classic D10 Nano kit and pressure and flex sensors, multi-channel analog to digital converter, and Bluetooth. And the software is the Intel Quartus Prime Design software. And you can see that now you have a Terasic D10 Nano, you have an ADC channel. And with the FPGA and HPS, we are trying to communicate. What is the advantage of the SoC and what expansions are there? These informations you can get it. So this is one set of project. Like that, there are multiple things that are explained in the presentation. So you can go through that. Even in the site, what I showed you, you have multiple examples. This is one more important example, which is on CNN. So acceleration of machine learning workload. For this, what we do is we use the CNN, which is the convolution neural networks. You have a camera and you have, it uses the object or face recognition. And then you have an FPGA based acceleration where we use a Cyclone Pay SoC FPGA and then ARM hard processor system plus OpenCL. And you can see object of classification. But along with the board, you require an 8 GB micro SD card, USB camera, Ethernet cable, and then we use OpenCL and Intel Quartus Prime Design software. So now with this, you can see how that could be possible. So these are different projects that are available. You can refer into it. Where you can get more details is from our Intel Terasic D10 Nano site page only. Not only these kind of applications, we can use it for self-guided vehicle, digital music synthesizer, edge detection algorithm, heartbeat monitoring system, smart traffic light control system for congested roads, tic-tac-toe, hardware in-loop simulation, smart home security system, intelligent traffic sign detection system, pothole detection system, ADAS using deep CNN on FPGA platform, crack detection system for hydraulic dams. Like that, there are sample applications that are available, which you can use it with respect to SoC FPGAs. Okay, so where you can get more details is directly we can go to our Intel Developer Zone. You will get more details about the D10 Nano. So you can directly go here, Intel Developer Zone, D10 Nano. So this will take you to the page where you have the entire details about the Terasic D10 Nano. So overview, and then what are the kind of industrial use cases, what are the code samples, and you can see that what are the compatible accessory cards, and you can see what are the different set of information, tutorials, projects. If you click this link, it will take you to the project which I have explained, where you can do, using these SoCs, we can do multiple mini projects. This is what you can see the list here, projects. So this is the project which is available here. And when you go through the Terasic D10 Nano site, okay, there also you can get more details. Okay. Inside the Terasic website, as I showed, right? Here also what you can do is, instead of D1 SoC, you can open the D10 Nano. Here you can go to DE boards, or you can go to SoC platform only. And here you select the D10 Nano. Instead of selecting the D1 SoC, you can select the D10 Nano. Inside the D10 Nano kit, you can go to the resources, and here you can download the documents, CD-ROM. If you download this D10 Nano CD-ROM, you will have all the examples. And you can see all the data card demonstrations which I showed. Everything is available in this page. So one is the rocket boards, and the second one is the Terasic, And the third one is the Thoracic DE10 Nano Intel Developer Zone. In these particular pages, you will have multiple details related to SoC design. And you have a specific project page, as I mentioned, right? You can use this and do multiple projects. So these are some example projects. Based on that, we can create our own project. There was a question on how to select. Okay, so here if you see, you don't need to select everything here. So there are multiple boards here. We wanted to select only the Cyclone 5 SoC board. Okay, so now I'd say here, just select Ultra. Okay, Ultra Cyclone 5 SoC board. Now you can see there are multiple examples here. You don't need to worry about the tool version, everything. Just to take one example, and you can get the idea like how do we use this. Okay, so for example, LED blinker is one example. You can click that LED blinker. It has the introduction, requirements, preparation, board configuration, all the details now. And how do we connect it? All these informations are provided step by step. So similarly, if you didn't select this, right, you have multiple examples. It can show ARIA 10, okay, DE10 nano. For example, if you wanted only DE10 nano, just click that DE10 nano. And you have multiple examples related to only DE10 nano, which I showed you some time back, right? This is a very good example. Like you can say simple line follower robot using SoC FPGA. So there is the, okay, you can see the video and you can see how that has been performed. The entire details are available here. Okay. And if you click the documentation section here, right, just click getting started. This is the place which I asked you to go through in the morning, right? So in this particular documentation portal, you have example designs on the right hand side. And you have reference design here. You can see there are how many reference designs are there. You can just have a look. This is for the Cyclone 5. Okay, documentations are there. And you can also see like tasks and tutorials. If you click here, you can see the different tutorials. You can click one link and then we can work. Okay. So you want to find a document, you can just click which document you want to click. This is with respect to boards and this is with respect to projects. Just click project will automatically take you. Okay. The moment you click this, you can see getting started. So in the getting started in the golden system reference design documentation, all the four are available, but then it is better to start with Cyclone 5. Once you have done it, then go to ARIA 10, then statics, then Agilex weekend. Okay, so here you can just select which board you want, which version. If you want to just select that, okay, for example, I say here, Altera 10, right? It is an ARIA 10 SoC board. Then you can see which version you want. And then you can just say whether you wanted only compiling the hardware design. First, I wanted to understand only the hardware design. Just say continue. You can select that. Okay, so first start with this and then you can click here prerequisites and compiling the design, converting the all the steps are explained here. Just go through that step by step. First click this, then you can see what particular operations need to be done. Complete the platform designer and then continue. Complete the Partus Prime design software and you can see this. All the things are explained step by step here. And there is one more place where you can get the reference design, which is our design store for Intel FPGAs. So go to Dev Store for Intel FPGAs, which is our design store. There are multiple examples related to SoC FPGAs. I can show that to you. So you can go to this page. I'll stop sharing and share that with you. Okay. Now here, select Intel Cyclone. Here you can see there are multiple examples. And you can filter it for the Cyclone 10 GX or Cyclone 10 LP, or you can also go through the D1 SoC or D10 Nano. Okay, so here you can get the logic. For example, you wanted to know newest or oldest, that you can take it. But what are the different examples I will show you, which are important for us? Okay, let me explain that to you. So I will show you some good projects which you can use it. So there are based on Cyclone 5. So you can see the Cyclone 5. NIAS 2 plus QC's Hello World Lab is there. Then UART RS32. And you have multiple examples related to Cyclone 5. Here you can see video and image processing design example and DVI display. And remote system upgrade, RSU design example. And Cyclone 5, which is D1 SoC board. This is a very good example. Accelerated FAR filter with the built-in direct memory access examples. So this, if you go through. So it is based on the FAR design. And then we use the DDR3 SDRAM. So this you can try. So it uses all the details here. So this is a very good reference design which you can try. So it is an accelerated FAR filter design. So this is also based on Cyclone 5. If you wanted to refer it to the documentation, it is here. The accelerated FAR with built-in DMA user guide. You can click this user guide. This will take you to the entire project here. So you can see the block diagram. Okay, which uses the NIAS 2, then slow peripheral bridge, JTAG UART, DDR3 controller. And this is our top level picture. And you need to follow the steps here because you have the FPGA as well as the hard processor system, because it is Cyclone 5. Then you can complete the DMA comp. So in each and every project, you have the documentation. This also you can refer. There are multiple places where you can have the reference design, where you can use it for performing mini project using the Intel SoC FPGAs. Okay, the first one is design center, that is the design center for Intel FPGAs. The second one is the Thoracic. Third one is the Rocket Boots. And fourth one is our Intel Developer Zone. In all these places, you can get more information about SoC FPGAs and how do we perform mini project using those SOC FPGAs. feel the timing would be by 4:30 p.m. I hope people can still confirm it.
Yes, sir. We are here till 4:30. From 4:30 p.m. we will be having one MCQ.
Right. So that's what they were asking, the timing of the quiz. So I told them that it would be 4:30. Am I right?
Yes, sir.
Okay. Right. Yeah. So there was a question in the chat related to the online training in the Intel SoC FPGA. I have already given details to that, but still I can just show that to you. This is a 40 minutes online course which explains about the hardware design flow for ARM-based Intel SoC FPGA. I will share this link in the chat, and I request you to just go through that because this will provide you details on how do we use that. Okay, so now this has you can see this particular online training will have Intel SoC FPGA using the Intel Cortex Prime design software as well as the platform integration tool. Both you can see that. And understand the necessary steps to create a custom component and run a functional simulation. And you can also debug using the system console tool. So all these informations have been covered, but I request you to go through this online training. This will have multiple informations related to that. And regarding the high-level synthesis training also, I showed you that day about online trainings. So high-level synthesis Intel online training. But then there was a query, so I will explain about that also. As I mentioned, there are 7 parts of the training. Here you can see part 1 of 7. So there are 7 parts of the training, so you can complete it one by one. It's a 65 minutes e-learning course. If you directly see that in the YouTube also, you can see all the parts one by one. You can see here, Introduction to High-Level Synthesis, part 1 of 7. And you can just go through that one by one. Okay, so the online trainings are available. That would be definitely helpful for you. Okay, so I will just share this link also on the okay. It will be starting by 4:30. You can wait for another 3-4 minutes. Okay, so it would be from 4:30 to 5 p.m. There will be 25 questions and then you will have 30 minutes.
Dear participants, you please check the drive if we have shared the link to the Google quiz MCQ2.